On July 1, 2025, at precisely 3:47 Universal Time, a sequence of automated alerts began cascading through the Atlas survey network in Chile. The pixels on the detector told a simple story. Something new had appeared in the southern sky. But only in the late hours of that night, as astronomers cross-referenced orbital parameters against every known object in our databases, did the true nature of the visitor reveal itself. The object now designated 3E Atlas was traveling on a hyperbolic trajectory, eccentricity greater than 1, hurtling through our solar neighborhood at approximately 44 kilometers per second. That's faster than any comet humanity has ever cataloged in 4 centuries of systematic observation. The third confirmed interstellar visitor in recorded history. The first two, Oumuamua and Tuai Borisov, had each rewritten portions of our understanding. Now, with 3I Atlas, we face something larger, brighter, and chemically stranger than either predecessor. Why now matters. Perihelion, the comet's closest approach to the Sun, already passed on October 29. Its nearest point to Earth is scheduled for December 19, 2025, just days away as this narrative unfolds. After that, 3I Atlas will fade beyond the detection threshold of even our most powerful instruments, disappearing forever into the interstellar void. This narrow window, these few months between discovery and departure, represents humanity's only chance to probe the secrets locked within this wanderer from another star system. Yet even as telescopes across 6 continents swiveled to track it, a vivid anomaly emerged. Infrared spectroscopy from the James Webb Space Telescope revealed a coma dominated not by water vapor, the hallmark of solar system comets, but by carbon dioxide. The Q to HEO ratio triggered immediate discussions among planetary scientists. In a cosmos governed by chance and physics, this icy body may carry chemical signatures shaped in the protoplanetary disk of a distant star, or perhaps something more. Before we go deeper into this mystery, hit like, subscribe, and tell me where you're listening from, because this story is still unfolding in real time, and your engagement helps us continue documenting these extraordinary moments in human exploration. This is not science fiction. This is December 2025. And now, we begin at the beginning. The night the universe sent us a message we're still learning to read. Chapter 1, July 2, 2025. Discovery of an interstellar visitor. July 2nd arrived quietly in Hawaii, where the central processing hub for the asteroid terrestrial impact last alert system operates in perpetual vigilance. Atlas, composed of 4 robotic telescopes scanning the entire accessible sky every 24 hours, exists for one primary purpose: to identify potentially hazardous asteroids on collision courses with Earth. But on this particular morning, the system flagged something that made no sense within the framework of solar system dynamics. The preliminary orbital solution, calculated by automated algorithms and then verified by human eyes, showed an eccentricity of approximately 1.4. In orbital mechanics, any eccentricity above 1 defines a hyperbolic trajectory, an object not bound by the sun's gravity, passing through our system just once before returning to interstellar space. The computers had seen this signature only twice before in modern astronomical history. Dr. Larry Deno, a principal investigator with the Atlas project, was among the first to examine the data stream. In an interview conducted weeks later, he described the moment with characteristic understatement. You run the numbers 3 times. You check for software errors. Then you start going through the archive footage to see if we missed it on earlier passes. The object had been visible for weeks, it turned out. Faint, moving slowly against the background stars, dismissed by preliminary filters as probable main belt asteroid noise. The archives yielded pre-discovery images dating back to late May 2025. Faint streaks on survey plates, barely distinguishable from cosmic ray hits and detector artifacts. But when processed with the correct orbital elements, those streaks aligned perfectly. 3E Atlas had been silently approaching for months, unnoticed, like a message in a bottle drifting across an ocean no one thought to scan. By the afternoon of July 2nd, orbital integrations placed the object's origin far beyond the heliopause, the boundary where solar wind yields to interstellar medium. Trajectory reconstructions suggested an entry velocity relative to the local standard of rest around 25 kilometers per second. Not fast by interstellar standards, but unambiguous in its implications. This was no escaped Oort cloud comet, no long-period wanderer from our sun's distant halo. This came from somewhere else. The distance at discovery, approximately 670 million kilometers from Earth, roughly 4.5 astronomical units. For scale, that places it somewhere between the orbits of Mars and Jupiter, at the moment of confirmation. Still far enough that surface features remained unresolved, but close enough that photometric measurements could begin establishing basic physical properties. And here the first surprise emerged. Standard photometry, measuring the brightness of the object across multiple wavelengths, suggested a nucleus several kilometers in diameter. Perhaps 3, perhaps 5, perhaps larger. The uncertainty bands were wide, dependent on assumptions about reflectivity, but even conservative estimates made 3I Atlas substantially bigger than Toy Borisov, the previous interstellar comet, which measured only about a kilometer across. Oumuamua, the first known interstellar visitor discovered in 2017, was estimated at just a few hundred meters. If these preliminary size estimates held, 3I Atlas would be the largest confirmed interstellar object ever detected passing through our solar system. That alone justified the mobilization of observational resources that followed. But size wasn't the only curiosity. The brightness fluctuations, changes in reflected sunlight as the object rotated, showed no clear periodicity in the early data. Typical comets and asteroids exhibit predictable light curves as they spin, with peaks and troughs corresponding to different surface facets catching sunlight. 3I Atlas displayed something messier. Irregular variations, possibly indicative of complex rotation, or an irregular shape, or active outgassing even at this considerable distance from the sun. Outgassing. That word carried weight. Comets are defined by their activity, ice sublimating into gas, as solar heat penetrates the surface, creating the characteristic coma and tail. But conventional models predicted minimal activity at 4 astronomical units for a typical comet. Water ice, the most abundant volatile in solar system comets, doesn't sublimate significantly until an object crosses roughly 3.0, closer to the sun where temperatures rise above the threshold for water's solid-to-gas transition. Yet here was 3I Atlas, already showing a faint coma in high-resolution images, captured by larger ground-based telescopes in the nights following discovery. A diffuse cloud of gas and dust, barely visible, but unambiguously present. Something was driving activity far earlier than solar heating alone should permit. This anomaly sparked immediate interest. Either the comet was extraordinarily volatile-rich, loaded with substances like carbon monoxide or carbon dioxide that sublimate at much lower temperatures than water, or something else was at play. Internal heat from radioactive decay, tidal stresses from a close pass by another star before entering our system, or perhaps a composition so radically different from solar system norms that our models simply didn't apply? Dr. Michele Bannister, a planetary astronomer specializing in small body dynamics, commented in an early press briefing, "When we see activity this far out, it tells us we're dealing with chemistry that isn't just frozen water. This object formed somewhere with different conditions, different ratios of elements, different temperatures, maybe different radiation environments over billions of years. Every measurement is a clue to processes we've never directly observed." Wanin Pachina. The scramble began. Observing time on major telescopes is allocated months in advance through competitive proposal processes, but 3 Atlas triggered directors' discretionary time. Emergency allocations reserved for transient phenomena. The European Southern Observatory's very large telescope in Chile, the Keck Observatory in Hawaii, the Subaru telescope, even the Hubble Space Telescope, all began slotting observation windows into their schedules. Meanwhile, the backlog of detection images was scrutinized frame by frame. Citizen science projects, volunteer astronomers sifting through archival data, identified additional pre-covery sightings. One enthusiast in Australia found a faint trace on an image from mid-May. Another, in Germany, flagged a possible detection in early June. Each sighting refined the orbital solution, narrowing the uncertainty in 3I atlases, past trajectory and future path. And the future path held particular significance. Integrating the orbit forward showed perihelion, the closest approach to the Sun, would occur on October 29, 2025, at a distance of approximately 1.36 astronomical units, just slightly beyond Earth's orbit. Close enough for intense solar heating, but not so close as to risk complete disintegration, the fate of many sun-grazing comets. After perihelion, 3E Atlas would swing outward again, passing relatively near Earth on December 19th, at a distance of roughly 170 million miles, 0.910, closer than the Sun, though still far beyond any collision risk. But December 19th represented more than just a geometric curiosity. It marked the last practical opportunity for high-resolution observations before the comet faded beyond magnitude limits. Every telescope on Earth would have a single, final chance to capture spectra, image the coma and tail, measure particle densities, and attempt to answer the most fundamental question: what exactly is this thing made of? In the history of astronomy, only 2 other interstellar objects had offered such opportunities. Oumuamua appeared and vanished so quickly that only basic photometry was obtained before it receded. Borisov gave more time, allowing spectroscopy that confirmed its cometary nature: water vapor, cyanide, diatomic carbon. But it was faint, distant, and difficult to study in detail. 3 Atlas, by contrast, was brighter, larger, and following a trajectory that brought it close enough for unprecedented measurements. As July 2nd turned into July 3rd, and then into the weeks that followed, the initial data packets began transforming into scientific papers. The discovery paper, formal confirmation of the interstellar nature and orbital characteristics, was drafted, peer-reviewed in accelerated fashion, and submitted to the astrophysical journal Letters. Press releases went out from NASA, the European Space Agency, and national observatories. The public learned, in simplified terms, that a visitor from another star system was passing through our cosmic neighborhood. But for the scientists tracking 3 Atlas, the real work was only beginning. Every night the comet was above the horizon. Telescopes locked onto its faint glow, collecting photons that had traveled light years to reach us, only to be reflected one final time off the surface of an ancient frozen body before entering our power instruments. Those photons carried information encoded in wavelengths: molecular fingerprints, thermal signatures, polarization states, data that would, over the coming months, gradually reveal the nature of this silent traveler. And already, in those early July observations, hints of deeper strangeness were appearing. The spectral lines, though preliminary, didn't quite match the templates for typical comets. The brightness variations defied simple models. The coma's diffuse glow suggested complexity in the outgassing pattern. Possibly multiple active regions, possibly compositional heterogeneity. None of this was conclusive. Not yet. But in the careful measured language of peer-reviewed science, the discovery papers ended with the standard phrase: further observations are required. And behind that phrase lay urgency. Because unlike asteroids, which orbit predictably and can be revisited year after year, 3 Atlas would make one pass and disappear forever. The clock was ticking. July 2nd, 2025, was the day we learned we had a visitor. But the story of what that visitor meant, for our understanding of planetary formation, for the prevalence of organic chemistry in the galaxy, perhaps even for the question of whether intelligence exists beyond Earth, that story was only just beginning to unfold. Chapter 2, late July 2025, First Spectra, Chemistry from Afar. By the 3rd week of July, 3 Atlas had brightened sufficiently for spectroscopy, a technique that splits incoming light into its component wavelengths, revealing the chemical composition of the object's atmosphere. It's one of the most powerful tools in astronomy, allowing scientists to identify molecules at distances where physical samples are impossible. And for an interstellar comet, spectroscopy offers the only realistic method to probe what ices formed in another star's protoplanetary disk billions of years ago. The first high-quality spectra came from the UV spectrograph on the Very Large Telescope in Chile, captured during a series of exposures on the nights of July 21st through 23rd. Dr. Alan Fitzsimmons, who led the observing team, described the data in an interview as immediately perplexing in its ordinariness, and yet subtly wrong. The spectra showed emission lines corresponding to several expected molecules. Carbon monoxide, CO, appeared prominently, its characteristic ultraviolet bands unmistakable. Water vapor, HO, was present, though weaker than typical solar system comets at equivalent distances. Dust continuum radiation indicated small particles scattering sunlight, consistent with sublimating ices dragging microscopic grains off the nucleus surface. All of this matched, broadly, what cometary science predicts, but the ratios were off. Carbon monoxide, in particular, was far more abundant relative to water than models anticipated. In solar system comets, especially those originating in the Oort cloud, water dominates the volatile budget by a significant margin, typically 10-to-1 or greater compared to company. Here, in 3A Atlas, the ratio appeared closer to parity, or perhaps even inverted depending on how the measurement uncertainties resolve. Why does this matter? Because molecular ratios encode formation history. Water ice condenses from the protoplanetary nebula at relatively warm temperatures, above 150 Kelvin or so, depending on pressure. Carbon monoxide, by contrast, requires much colder conditions to freeze out, below roughly 30 Kelvin. A comet rich in CO relative to water suggests formation in the frigid outer regions of a planetary system, or perhaps in an environment where carbon chemistry dominated over oxygen-water chemistry. But there's another possibility, one that several researchers raised in the preliminary discussions following the spectroscopic release. Carbon monoxide can also be produced by the irradiation of more complex carbon-bearing molecules. Cosmic rays, ultraviolet starlight, and high-energy particles can break apart organic compounds, leaving simpler volatiles like CO as remnants. If 3 Atlas spent millions or billions of years drifting through interstellar space, exposed to the harsh radiation environment between stars, then its surface chemistry could have been significantly altered from its original state. This degeneracy, the inability to distinguish between primordial composition and radiation process composition, frustrates efforts to draw firm conclusions. Both scenarios fit the data. Both are physically plausible. And without direct samples or close-up imaging, teasing them apart requires indirect inference and modeling. The presence of water vapor, though subdued, provided its own clues. Water's emission lines in the spectrum indicated sublimation rates on the order of a few kilograms per second at this distance. Not a dramatic outburst, but steady, persistent activity. That implies surface ices accessible to solar heating, despite the comet being over 600 million kilometers from the Sun. Either the surface is unusually porous, allowing heat to penetrate and release deeper volatiles, or patches of the nucleus have low thermal inertia, perhaps freshly exposed material from recent fragmentation or outbursts. Cyanide radicals, CNA, also appeared faintly in the spectra, another common cometary molecule. Cyanide forms from the photodissociation of more complex nitrogen and carbon compounds, and its presence is typically interpreted as evidence of organic chemistry. Every comet ever studied in detail has shown CN emission. 3I Atlas fit that pattern, suggesting at least some overlap in chemical inventory with solar system analogs. Yet, the overall emission profile remained anomalous. Normally, cometary spectra at this heliocentric distance would be dominated by water and its dissociation products, hydroxyl radicals, hydrogen atoms. Here, the carbon-bearing species held comparable or greater prominence. It was as though the comet's chemistry was inverted, carbon-rich where it should be oxygen-rich. Dr. Karen Meek, a comet researcher at the University of Hawaii who had studied Tuohy-Borisov extensively, offered perspective in a public seminar. We're looking at chemistry that doesn't fit cleanly into our solar system's boxes. That's exciting, because it means this object can teach us about conditions in another planetary system. But it's also humbling, because we realize how limited our sample size is. 2 interstellar comets, now 3. It's not enough to build a robust theory. Everyone is a data point, but we need dozens to understand the population. The early spectroscopy also raised questions about activity mechanisms. At over 4 astronomical units, solar flux is weak, only about 6% of what Earth receives. Water ice doesn't typically sublimate at those temperatures. And yet, 3I Atlas was clearly outgassing. Carbon monoxide, with its much lower sublimation temperature, could be the driver. As CO sublimated from the nucleus, it could entrain dust and other volatiles, creating a coma even in the absence of significant water activity. This co-driven outgassing model has precedent. Some solar system comets, particularly those visiting from the distant Oort cloud for the first time, show early activity dominated by hypervolatiles like CO, cono, and methane. As they approach the sun, water eventually takes over as the primary driver. If 3I Atlas follows a similar pattern, then the spectra captured in late July represent a snapshot of an early carbon-dominated phase, with water activity expected to increase as perihelion approaches. But there's also speculation, more tentative, less grounded in established comet science, that 3I Atlas could be fundamentally different. Some researchers, particularly those studying interstellar dust and chemistry, have proposed that objects forming in metal-rich or radiation-intense environments might incorporate unusual materials. Iron-nickel grains, for instance, embedded in ice matrices, or complex organic tars produced by radiation polymerization. These materials could alter thermal properties, outgassing behavior, and spectral signatures in ways not accounted for by standard models. One preprint paper, posted to the arXiv repository on July 28 by a team led by Dr. Daryl Seligman at Cornell University, explored this hypothesis in detail. The authors constructed models where metal grains mixed with carbon-rich ices undergo internal chemical reactions, catalytic processes similar to Fischer-Tropsch synthesis, as solar heating raises internal temperatures. Such reactions could produce gases not present in the original ice, including methane, ethane, and more complex hydrocarbons. The paper was careful to emphasize that no direct evidence yet supported this exotic chemistry. But it laid groundwork for interpreting future observations, particularly if unexpected molecules appeared in spectra as 3I Atlas approached perihelion. The mere fact that such models were being seriously considered indicated how far outside the norm this object was pushing researchers. By the end of July, multiple observing campaigns were underway. Radio telescopes joined optical and infrared instruments, searching for emission from molecules like methanol and formaldehyde that might be present in trace amounts. The Hubble Space Telescope captured high-resolution images of the coma, revealing its roughly symmetric morphology. No obvious jets or asymmetries visible yet, just a diffuse glow. The James Webb Space Telescope scheduled its first observations for early August, targeting specific infrared wavelengths, where carbon dioxide and water vapor have strong absorption and emission features. Each dataset added pieces to the puzzle. But the puzzle itself remained incomplete, its final image unclear. The spectroscopic data from late July suggested an object rich in carbon and depleted in water relative to expectations. That chemistry implied formation conditions different from the solar system's own history. Perhaps a star system with a different carbon-to-oxygen ratio, or a region of the protoplanetary disk where temperatures and pressures favored carbon-bearing ices over water ice. Or it implied a long interstellar journey that baked, irradiated, and chemically transformed the surface into something no longer representative of the original composition. Distinguishing these possibilities required more data, deeper spectra, broader wavelength coverage, thermal measurements. And time was passing. Each day, 3I Atlas moved closer to the sun, its activity increasing, its coma brightening. The early spectroscopy captured a relatively quiescent phase. What would the comet reveal as solar heating intensified? Would water begin to dominate, or would carbon chemistry continue to rule the spectrum? Would new, unexpected molecules appear, signatures of processes unknown in our solar system? The answers were weeks away. But already, in those first spectra from late July, the message was clear. 3I Atlas was not just another comet. It was a chemical anomaly, a frozen archive from another star's history, offering a glimpse into the diversity of planetary systems across the galaxy. And it was only just waking up. Chapter 3. August 2025. Infrared Revelation, a home-rich coma. The moment the astronomical community had been anticipating arrived on August 7th, when the James Webb Space Telescope released its first infrared spectrum of 3 Atlas. The data, captured using the near-infrared spectrograph over a 6-hour observation window, transformed the conversation from uncertainty to revelation. Carbon dioxide in quantities that rewrote the narrative. The spectrum showed a strong absorption feature at 426 microns, the unmistakable signature of co-molecules vibrating in the comet's coma. The intensity of the feature, when modeled, suggested that carbon dioxide was the dominant volatile species, outstripping water vapor by a factor between 2 and 5, depending on the assumed temperature and density distribution. This was not a subtle hint. This was a blaring signal. Dr. Stephanie Milam, Deputy Project Scientist for Planetary Science at NASA Goddard, summarized the implications in a press briefing. We've never seen a comet, interstellar or otherwise, with a Con to HO ratio this extreme. In our solar system, even the most carbon-rich comets still have water as the primary driver of activity. Here, water is almost a secondary component. That tells us this object formed under very different thermochemical conditions. To understand why this matters, it helps to revisit the basics of planetary formation. When a star ignites from a collapsing molecular cloud, it's surrounded by a disk of gas and dust, the protoplanetary disk. Temperature gradients in the disk determine which substances condense into solid particles at different distances from the star. Close to the star, only high-temperature materials like silicates and metals can remain solid. Farther out, water ice condenses, dramatically increasing the available solid material, the so-called snow line. Beyond that, at even colder distances, carbon dioxide, methane, and other volatiles freeze out. A comet rich in Cu, relative to water, suggests formation in the outer reaches of such a disk, beyond where water was the dominant ice. Or it suggests formation in a disk where the carbon-to-oxygen elemental ratio was higher than our Sun's, shifting the chemistry away from water-dominated systems toward carbon-dominated ones. Stellar systems vary in their elemental abundances. Stars that formed from molecular clouds enriched by earlier generations of supernovae, particularly type Ia supernovae that produce carbon and oxygen in specific ratios, can have different carbon-to-oxygen ratios than our Sun. If 3 Atlas originated around a carbon-rich star, its protoplanetary disk would have favored the formation of carbon-bearing molecules and ices over water ice. The COH coma could be a direct fingerprint of that alien environment. But there's another interpretation, one that several papers published in August began to explore. If 3I Atlas spent tens or hundreds of millions of years, or even billions of years, drifting through interstellar space, cosmic ray bombardment could have chemically processed the surface ices. High-energy particles can break apart water molecules, liberating oxygen atoms that then react with carbon monoxide or organic compounds to form carbon dioxide. Over immense timescales, this could deplete water and enrich cone on the surface layers. This radiation processing hypothesis gained traction because it could explain both the carbon dioxide abundance and the earlier spectroscopic findings of strong CO emission. If the surface had been irradiated for eons, simpler molecules like Ko and Con would accumulate while more complex organics and water were gradually destroyed. The challenge, though, was timescale. The efficiency of cosmic ray processing depends on the flux of high-energy particles, which varies depending on the comet's path through the galaxy. Detailed models, published as preprints throughout August, struggled to produce the observed Con-HO ratio through radiation alone within plausible transit times, unless the comet had traveled for over 1 billion years. A billion-year journey. The number is staggering. 3 Atlas, if this scenario holds, could have been ejected from its home star system long before Earth's multicellular life evolved, drifting in the cold darkness while dinosaurs rose and fell, while our ancestors learned to make fire, while human civilization emerged and began turning telescopes toward the sky. And only now, by chance, did its trajectory intersect with ours. The James Webb data also revealed subtler details. Water vapor was present, confirmed by absorption features at 2.7 microns, but the emission strength was weaker than Ku by that factor of 2 to 5. Trace amounts of methane, CHIC, appeared in the spectrum as well, though near the detection limit. Its presence tentative but intriguing. Methane, like carbon dioxide, forms under cold conditions and can be produced through both primordial condensation and radiation-driven chemistry. Its detection, if confirmed by follow-up observations, would add another piece to the chemical inventory. The coma's infrared brightness also allowed researchers to estimate the outgassing rate more precisely than earlier optical measurements. The models suggested that 3E Atlas was producing roughly 50 to 100 kilograms of gas per second at the time of the Webb observations, mostly carbon dioxide, with lesser contributions from CO and water. This placed the comet's activity level on par with moderately active solar system comets at similar distances, though the chemical composition remained strikingly different. Thermal modeling based on the infrared emission indicated a surface temperature around 180 to 200 Kelvin, cold by terrestrial standards, but warm enough to drive sublimation of co-ice, which transitions from solid to gas at about 150 Kelvin under near vacuum conditions. Water ice, by contrast, doesn't sublimate efficiently until temperatures exceed 200 Kelvin. The comet was living in a thermal zone where carbon dioxide outgassing dominated, with water only beginning to contribute meaningfully. This thermal regime suggested that as 3E Atlas continued its approach toward perihelion, the balance might shift. If solar heating pushed surface temperatures above 200 Kelvin uniformly, water vapor production could increase dramatically, potentially equalizing or even surpassing Con. Or if the nucleus was stratified, layers of different compositions, then the surface chemistry might not reflect the interior. Deeper ices, shielded from radiation processing, could be richer in water and organics, waiting to be revealed as the outer layers eroded away under solar heat. These questions drove further observations. Additional Webb time was requested and approved for early September, targeting the same infrared wavelengths to monitor changes as the comet neared perihelion. Ground-based telescopes continued optical and ultraviolet spectroscopy, tracking the evolution of CN, CO, and O emissions. The goal was to build a time series, a movie, in effect, of how 3N Atlas's chemistry evolved under increasing solar radiation. But amid the scientific excitement, a quieter realization settled in. The cone-dominated composition was, in itself, a profound discovery. It demonstrated that interstellar comets could be radically different from their solar system counterparts, not just in trajectory, but in fundamental chemistry. This diversity implied that planet formation processes vary more than theories had allowed. It suggested that the galaxy might be filled with populations of comets, each population shaped by the unique history of its parent star system. Metal-rich or metal-poor, carbon-rich or oxygen-rich, young or ancient. Every interstellar visitor offers a window into that diversity. Oumuamua, with its elongated shape and non-gravitational acceleration, hinted at complex dynamics. Toy Borisov, with its familiar water-rich coma, suggested commonality. And now 3I Atlas, with its carbon dioxide dominance, revealed difference. 3 data points, 3 different stories. The population statistics remained too sparse for confident generalizations, but the hint was clear. The galaxy's comets are more varied than our solar system's sample suggests. Dr. Kathleen Mant, a planetary scientist specializing in volatiles and atmospheres, wrote in a commentary published mid-August, 3 Atlas forces us to expand our definitions. We've thought of comets as dirty snowballs, water ice mixed with dust and a little CO and con. But what if, in some star systems, they're carbon dioxide ice mixed with a little water? The physics is the same, but the chemistry is inverted. That inversion has implications for how we think about habitable zones, organic delivery to planets, the distribution of life's building blocks across the galaxy. The implications stretched beyond cometary science. If carbon dioxide-rich bodies are common in other systems, then the delivery of volatiles to rocky planets during late-stage bombardment could be chemically different than Earth's history. Earth's water likely came, at least in part, from cometary and asteroid impacts. But if those impactors had been cov-rich instead of water-rich, the resulting planet might have developed a thick carbon dioxide atmosphere, like Venus, rather than liquid water oceans. The balance between water and Ku in the volatile inventory of a young planet could determine whether it becomes a paradise or a hell. This line of thinking remained speculative, extrapolated far beyond the data, but it illustrated how a single comet, observed for a few weeks, could seed ideas that propagated through multiple disciplines: astrobiology, planetary atmospheres, galactic chemical evolution. As August drew to a close, 3A Atlas continued its inward journey. The carbon dioxide finding had been absorbed by the scientific community, dissected in seminars and colloquia, debated in email chains and preprint comment threads. Consensus formed around the reality: this was a con-rich comet, unprecedented in the observational record. Whether that richness reflected primordial formation or billions of years of radiation processing remained unresolved. Both possibilities were on the table. But one thing was certain. The August infrared revelation transformed 3 Atlas from a curious interstellar visitor into a keystone object, a comet that challenged assumptions, expanded taxonomies, and hinted at the vast chemical diversity awaiting discovery among the stars. And it was still approaching, still brightening, still revealing itself, molecule by molecule, spectrum by spectrum. Chapter 4. September 25. Polarimetry and unusual light behavior. September brought a different kind of observation, one that proves not chemistry, but structure. Polarimetry, the measurement of how light waves oscillate after reflecting off particles, offers insight into the size, shape, and composition of dust grains in a comet's coma. It's a technique that has been used for decades to study solar system comets, building a database of how different dust types produce different polarization signatures. And when polarimetric measurements of 3 Atlas came in during the first week of September, they didn't fit the templates. The observations were made using the Force 2 instrument on the European Southern Observatory's Very Large Telescope, capturing polarized light across visible wavelengths. The team, led by Dr. Ludmila Kolokolova at the University of Maryland, found something remarkable. 3 Atlas exhibited a deep negative polarization branch at phase angles, the angle between the Sun, comet, and observer, around 15 to 20 degrees. In polarimetry, negative polarization means that light waves oscillating perpendicular to the scattering plane are weaker than those oscillating parallel to it. Most solar system comets show this effect, but to a moderate degree. 3 Atlas's negative polarization was much stronger, reaching depths comparable to certain trans-Neptunian objects and some primitive carbon-rich asteroids. This signature typically indicates particles that are either unusually fluffy and porous, or composed of materials with specific refractive indices, like organic tars or amorphous carbon. Dr. Kolokolova commented in an interview, "The polarization tells us the coma dust isn't just ordinary silicate grains. There's likely a significant fraction of carbonaceous material, organic compounds, maybe complex polymers formed through radiation chemistry over long timescales. This matches the carbon-rich gas we've seen spectroscopically, but it extends that richness into the solid phase." The finding aligned with earlier hypotheses about radiation processing. If 3I Atlas spent eons in interstellar space, ultraviolet light and cosmic rays could have polymerized simple organic molecules on grain surfaces, building up layers of complex, carbon-rich tars. These tars, when entrained in the coma as the comet outgassed, would produce the observed polarimetric signature. It was another fingerprint of an ancient, wandering body, its surface chemistry shaped by the harsh environment between stars. But polarimetry revealed more than just composition. The data also showed that the coma was remarkably diffuse and symmetric. Typically, cometary comas exhibit structure, jets emanating from active regions on the nucleus, spiral patterns induced by rotation, asymmetries driven by uneven heating. 3I Atlas, by contrast, presented an almost featureless haze. No resolved jets. No obvious rotational modulation in the coma morphology. This lack of structure perplexed researchers. Jets are a hallmark of cometary activity, driven by localized sublimation from specific patches on the nucleus surface, often associated with areas of low ice coverage or high thermal conductivity. Their absence suggested one of two possibilities. Either the entire nucleus was uniformly outgassing, with no preferred active regions, or the nucleus was rotating so rapidly, or in such a complex manner, that any jets smeared out into a symmetric envelope. T. Follow-up: photometric monitoring. Throughout September attempted to resolve this ambiguity by searching for periodic brightness variations, evidence of rotation. And here too, 3I Atlas proved elusive. The light curve showed variability, but not clear periodicity. Some observers claimed hints of an approximately 16-hour cycle, but the signal was weak, buried in noise and complicated by the changing phase angle as Earth's position relative to the comet shifted. Dr. Beatrice Mueller, a dynamicist at the Max Planck Institute who analyzed the photometric data, remarked, "It's possible the nucleus is in a complex rotational state, tumbling, rather than spinning around a single axis. That would produce irregular light curves and smear out any jet features. Or the nucleus could be very irregularly shaped, with multiple lobes or fragments, each contributing to the scattered light in unpredictable ways." The idea of a fragmented or binary nucleus gained some traction. Several solar system comets are known to be contact binaries, two distinct lobes barely held together by weak gravity. If 3I Atlas had a similar structure, or if it was in the process of slowly disintegrating, the resulting light curve would indeed be chaotic. Fragmentation events are common among comets undergoing close solar passes, as thermal stresses crack and split the weak, porous nucleus material. But there was another, more speculative interpretation circulating in informal discussions. If the nucleus was unusually smooth and spherical, perhaps mantled by a thick layer of processed amorphous material, then rotational variations might be suppressed. A nearly featureless sphere would show minimal brightness changes regardless of rotation. This cloaked nucleus scenario was difficult to test without direct imaging, but it offered an explanation for both the featureless coma and the irregular photometry. Amidst these structural puzzles, the polarimetric data also hinted at particle-size distributions. The degree of polarization at different wavelengths allowed modeling of the dust grain sizes in the coma. The results suggested a population dominated by small particles, submicron to a few microns in diameter, consistent with freshly sublimated dust entrained by outgassing. Larger grains, millimeter-sized or bigger, appeared to be less abundant, though they couldn't be ruled out entirely. This size distribution resembled that of other active comets, suggesting that despite the chemical oddities, the physical mechanics of dust release were relatively ordinary. The September observations also coincided with efforts to measure the polarization of the gas emissions separately from the dust continuum. Certain molecules, particularly those fluorescing in ultraviolet light, emit polarized radiation depending on their excitation geometry. Early attempts to measure this gas phase polarization in 3 Atlas were inconclusive. The signals were too faint, but the technique remained on the observing agenda for later in the month, as the comet brightened. By mid-September, 3 Atlas had crossed inside 3 astronomical units, bringing it into the realm where water sublimation becomes significant. Spectroscopy from this period showed the first hints of increasing water vapor emission, though carbon dioxide still dominated. The hydroxyl radical, O, the primary photodissociation product of water, began appearing more prominently in ultraviolet spectra captured by the Hubble Space Telescope. The comet was transitioning, its chemistry evolving as solar heating intensified. The diffuse coma, meanwhile, continued to grow. High-resolution imaging from large ground-based telescopes, using adaptive optics to counteract atmospheric blurring, showed the coma extending roughly 100,000 kilometers from the nucleus, about 8 times the diameter of Earth. Within that envelope, faint streamers and filaments appeared in some images, possible hints of localized outgassing that hadn't yet organized into clear jets. But these features were transient, appearing in one image and absent in the next, making systematic study difficult. The polarimetric findings, deep negative polarization, carbon-rich dust, diffuse coma, painted a picture of an object covered in ancient, radiation-processed material, but they also left fundamental questions unanswered. What was the nucleus shape? How fast was it rotating? Was it solid, or a loose aggregate of fragments? Without a spacecraft mission, without close-up imaging and in situ measurements, these questions remained tantalizingly beyond reach. Yet the absence of clear answers didn't diminish the value of the data. Every polarization measurement, every photometric data point, contributed to a growing library of observations that future researchers would mine for insights. If another Cow-rich interstellar comet appeared in 10 years, or 50, or 100, the 3I Atlas dataset would serve as the comparison template, the prototype against which new discoveries would be measured. As September ended, the comet was less than 2 astronomical units from the Sun, speeding toward perihelion. The next phase of observation would focus on thermal measurements, tracking how the nucleus temperature responded to increasing solar flux, and searching for outbursts or fragmentation events. The polarimetry had revealed dust that was carbon-rich and fluffy, a coma that was diffuse and symmetric, and photometric behavior that defied simple interpretation. It was a portrait of an object shaped by time and radiation, carrying within it the signatures of processes and environments alien to our solar system. And as 3I Atlas drew closer to the Sun, it was about to wake fully, its ices vaporizing en masse, its secrets becoming harder to hide. Chapter 5, October 3, 2025, Mission Math and a Possible Rendezvous. On October 3, a paper appeared on the arXiv preprint server that shifted the conversation from passive observation to active intervention. The lead author was Dr. Amir Siraj, a postdoctoral researcher working with Professor Abraham Loeb at Harvard. The paper's title was modest, Trajectory Analysis for a Rapid Interstellar Object Intercept, but its implications were bold. Could humanity send a spacecraft to physically visit 3E Atlas? The idea wasn't entirely new. After Oumuamua's discovery, proposals had circulated for ultra-fast missions using solar sails or laser-pushed probes to chase down interstellar objects. But those concepts remained firmly in the realm of future technology, decades away from implementation. The Siraj-Loeb paper took a different approach. Could an existing spacecraft, already in space, perform a trajectory adjustment to intercept 3E Atlas? The math, as always, was unforgiving. Orbital mechanics dictates that changing a spacecraft's trajectory requires energy, delta V, in the jargon, and available delta V is limited by onboard fuel. Most deep space missions are designed with specific targets in mind, their fuel budgets allocated for arrival maneuvers, course corrections, and orbital insertions. Diverting to an unplanned target consumes reserves that may not exist. Siraj and Loeb ran simulations for several candidate spacecraft. The European Space Agency's Rosetta probe had successfully rendezvoused with a comet in 2014, but it exhausted its fuel and was deliberately crashed into the comet's surface in 2016, no longer an option. NASA's New Horizons probe, which flew past Pluto in 2015, was still operational and had some fuel remaining, but its trajectory through the outer solar system placed it far from any viable intercept path with 3I Atlas. The delta V required to bend its course inward was prohibitive. The Japanese Hayabusa mission, which returned a sample from asteroid Ryugu in 2020, was en route to a follow-up target, asteroid 1998 Chi-26, with arrival scheduled for 2031. Could it be diverted? The study estimated that reaching 3I Atlas would require roughly 1.5 kilometers per second of delta V, significantly more than Hayabusa's remaining fuel could provide. The probe would need to perform a powered flyby of Earth to gravitationally assist the maneuver, but the timing didn't align. 3I Atlas would be too far away by the time such a flyby could occur. The conclusion was sobering. No existing mission had the fuel, the trajectory, and the time to intercept 3I Atlas before it departed the inner solar system. The paper acknowledged this reality, but argued that the exercise was valuable for future preparedness. When another interstellar object appeared, having a rapid response mission architecture already designed and funded could make the difference between observation and exploration. Professor Loeb, in interviews following the paper's release, emphasized the opportunity cost of inaction. We're letting the third interstellar object in history pass through our solar system without attempting physical contact. Every day we develop more capable rockets, more efficient propulsion systems. If we committed resources now, we could design a mission capable of reaching the next interstellar visitor within months of discovery. But that requires foresight and political will. The paper sparked broader discussions within the planetary science community. Some researchers agreed wholeheartedly, arguing that interstellar objects represented a unique opportunity to study material from other star systems without the need for centuries-long interstellar voyages. Others pointed out the practical barriers: funding, risk management, the difficulty of designing a mission on extremely short timelines. NASA's Planetary Defense Coordination Office, tasked with tracking potentially hazardous asteroids, had considered rapid response architectures in the past. But those studies focused on threats, deflecting incoming impactors, not scientific exploration. The budgetary and engineering challenges of building a standby spacecraft, fueled and ready to launch at a moment's notice toward an unknown target, were immense. Still, the concept had advocates. Dr. Michelle Bannister, in a public talk at the International Astronomical Union's annual meeting that October, proposed a comet interceptor program, a small fleet of compact probes placed in high-inclination solar orbits capable of quick adjustments to rendezvous with passing interstellar objects. Think of it as a fire station for comets, she explained. You don't build the fire truck after the building is on fire. You have it ready, maintained, staffed, waiting. We need that for interstellar visitors. The European Space Agency, coincidentally, had a mission in development called Comet Interceptor, scheduled for launch in the late 2020s. Its design allowed for targeting long-period comets, making their first entry into the inner solar system, pristine objects that had never been heated by the sun. While not specifically designed for interstellar targets, the mission architecture could, in principle, be adapted. But it wouldn't be ready in time for 3 Atlas. The Cyragilo paper also explored more speculative propulsion technologies. Solar sails, which use photon pressure from sunlight to accelerate without fuel, could in theory reach high velocities given enough time. But deploying a sail, accelerating, and then intercepting a fast-moving interstellar object required precise timing and favorable geometry. The authors estimated that a sail-equipped probe might achieve an intercept within 2 to 3 years if launched immediately, too late for 3 Atlas, but feasible for future visitors if detection came early enough. Laser-pushed light sails, the concept championed by the Breakthrough Starshot initiative, offered even higher potential speeds. But that technology remained experimental, with enormous engineering hurdles related to sail material, laser power, and targeting accuracy. It wasn't a near-term solution. Public reaction to the paper was mixed. Enthusiasts saw it as a call to action, a reminder that humanity's reach could extend beyond passive telescope observation. Skeptics viewed it as impractical, a distraction from more immediate scientific priorities. Social media discussions ranged from supportive, "We should absolutely try this," to dismissive, "Not worth the cost when we have so many problems on Earth." Within the scientific community, the conversation was more measured. Interstellar objects were undeniably valuable, but so were sample return missions to Mars, deep space infrared telescopes, planetary landers. Resources were finite. Priorities had to be balanced. The question wasn't whether an interstellar intercept mission was scientifically worthwhile. It clearly was, but whether it was worth delaying or canceling other missions to fund it. As October 3rd passed into the following days, no space agency announced plans to divert a spacecraft. The math simply didn't work for 3I Atlas. But the conversation had been started. The technical feasibility studies existed. The groundwork was laid for future missions, should the political and budgetary environment shift. And there was another angle, one that Loeb had raised in previous works and interviews: the possibility that an interstellar object might not be natural. The idea remained controversial, resting primarily on Oumuamua's unusual acceleration, attributed by most scientists to outgassing, but argued by Loeb to potentially indicate artificial propulsion. If such a hypothesis held even a small chance of being correct, then the imperative to send a mission became not just scientific, but civilizational. For 3I Atlas, no similar anomalies had appeared. Its trajectory, while hyperbolic, followed predictable gravitational dynamics modified by standard outgassing forces. There were no signs of artificial acceleration, no geometric peculiarities like Oumuamua's elongated shape. 3I Atlas looked, in most respects, like a comet, albeit an unusual one. But the door remained open, however, slightly. And that openness, the acknowledgement that we don't yet know everything, that surprises remain possible, fueled the ongoing fascination. Not just among researchers, but among the wider public, for whom the idea that we might, just might, be observing something intentionally sent our way by another intelligence carried a profound allure. The October 3rd paper served as a reminder. Observation, however sophisticated, has limits. True understanding requires touch, sampling, probing, measuring up close. For 3I Atlas, that opportunity was slipping away. But the framework for future action had been sketched. And perhaps, when the fourth or fifth interstellar visitor appeared, humanity would be ready. Chapter 6. October 29th, 2025. Perihelion Passage, the Sun's Caress. October 29th, 2025, marked the pivotal moment in 3I Atlas's journey through our solar system. Perihelion, the point of closest approach to the Sun. At precisely 1422 Universal Time, the comet reached a distance of 1.36 astronomical units, roughly 204 million kilometers, from the solar surface. For context, that places it slightly beyond Earth's orbit, in a region where solar flux is intense enough to drive vigorous sublimation of water ice, carbon dioxide, and other volatiles embedded in the nucleus. This was the moment researchers had been preparing for. Perihelion passages are transformative for comets. The rapid heating experienced at closest approach can trigger outbursts, violent releases of gas and dust, as subsurface pockets of volatile ices suddenly vaporize. Structural weaknesses in the nucleus, previously stable, can fracture under thermal stress, leading to fragmentation. And the outgassing rate, already significant at greater distances, reaches its peak, creating the most dramatic and observable phase of cometary activity. For 3I Atlas, the weeks leading up to perihelion had shown steadily increasing brightness and coma expansion. By mid-October, the comet had brightened to roughly magnitude 9, still too faint for naked eye visibility, but easily accessible to amateur telescopes. The coma diameter, measured by wide-field imaging, exceeded 200,000 kilometers, nearly twice what it had been a month earlier. Spectroscopic monitoring showed water vapor production ramping up, beginning to rival carbon dioxide for the first time since discovery. But the perihelion passage itself brought surprises. The first came from the Solar and Heliospheric Observatory. SOHO, a spacecraft positioned at the lone Lagrange point between Earth and the Sun, perpetually monitoring solar activity. SOHO's coronagraphs, designed to block the Sun's direct light and image the surrounding corona, serendipitously captured 3I Atlas as it passed through the instrument's field of view. The images revealed a dramatic brightening. In the hours surrounding perihelion, the comet's coma flared, increasing in luminosity by a factor of 3 over the course of 6 hours. This wasn't an outburst in the classical sense. No discrete jets or fragment clouds appeared, but rather a surge in overall outgassing, likely driven by a large surface area of the nucleus suddenly crossing the thermal threshold for rapid water sublimation. Dr. Matthew Knight, a cometary scientist at the U.S. Naval Research Laboratory who analyzed the SOHO data, described the event. What we're seeing is the comet's response to the solar radiation pulse. At perihelion, the sun's heat penetrates deeper into the porous nucleus, vaporizing ices that were previously stable. That vapor expands violently, dragging dust with it, and the result is this temporary brightening. It's a comet's way of exhaling after holding its breath. Simultaneous observations from ground-based telescopes showed the spectral changes accompanying the brightening. Water vapor emission lines intensified dramatically. Hydroxyl radicals, O became the dominant feature in ultraviolet spectra, surpassing even CO and CO for the first time. Sodium emission, a signature of dust grains being vaporized by solar heat, appeared prominently in optical spectra. And cyanide, CNE, reached its peak intensity, indicating substantial organic material being released from the nucleus. The thermal infrared observations from the James Webb Space Telescope, scheduled for October 30th to capture the immediate post-perihelion state, showed surface temperatures spiking above 250 Kelvin in localized regions. This was hot enough to drive efficient water sublimation, and the infrared spectra confirmed the shift. Water vapor now contributed as much flux as carbon dioxide in the 3-5 micron wavelength range. The comet's chemical balance was tipping. But the most visually striking result came from imaging. High-resolution photographs captured by amateur astronomers across the globe, using backyard telescopes equipped with sensitive CCD cameras, revealed the development of a tail. Prior to perihelion, 3E Atlas's tail had been faint and diffuse, barely distinguishable from the coma. Now, post-perihelion, a distinct dust tail extended over 1 million kilometers, visible as a faint yellowish streamer pointing away from the sun. Alongside the dust tail, a fainter, bluish ion tail appeared, gas molecules ionized by solar ultraviolet radiation, then swept back by the solar wind. Ion tails are always directed radially away from the sun, while dust tails curve slightly due to orbital motion. The simultaneous presence of both tail types is a classic signature of an active comet, and 3I Atlas now displayed the full cometary repertoire. Polarimetric measurements taken on October 30th showed changes in the dust properties. The deep negative polarization branch observed in September had weakened, suggesting that the fresh dust being released at perihelion had different characteristics, perhaps less processed by radiation, more representative of pristine interior material. This shift supported the hypothesis that the pre-perihelion coma had been dominated by ancient surface material, while perihelion activity was tapping into deeper, less altered ices. Not all observations went smoothly. Several spacecraft in solar orbit, including some Mars orbiters, had been tasked with observing 3I Atlas during perihelion. But technical issues and scheduling conflicts limited the data acquired. The Mars Atmosphere and Volatile Evolution mission, MAVEN, attempted ultraviolet spectroscopy from its vantage point orbiting Mars. But the comet was too faint at that distance for high-quality spectra. The European Space Agency's Mars Express captured a few images, but geometry placed the comet nearly behind the Sun from Mars's perspective, limiting spatial resolution. Nonetheless, the coordinated observing campaign succeeded in assembling a multi-wavelength portrait of perihelion. Infrared, optical, ultraviolet, even some X-ray observations, each wavelength regime offering a different piece of the puzzle. X-ray emission, detected faintly by the Chandra X-ray Observatory, came from charge exchange interactions between solar wind ions and cometary gas, a process common in active comets but never before observed in an interstellar visitor. The outgassing rate at perihelion was estimated at approximately 500 kilograms per second, roughly 1,000 pounds every 2 seconds, vaporizing off the nucleus and escaping into space. Over the course of the perihelion passage, 3I Atlas likely lost tens of thousands of metric tons of material. For a nucleus estimated at several kilometers in diameter, with a mass potentially in the range of trillions of kilograms, this mass loss was a small fraction, but enough to significantly alter surface appearance and expose deeper layers. The question of fragmentation loomed. Many comets don't survive close solar passes intact. Thermal stresses crack the nucleus, tidal forces pull fragments apart, and the comet disintegrates into a swarm of smaller pieces that eventually disperse. Famous cases include Comet Shoemaker-Levy 9, torn apart by Jupiter's gravity in 1992, and Comet Ison, which disintegrated during its 2013 perihelion. But 3I Atlas showed no signs of breaking up. The photometric light curve remained relatively smooth, without the sudden drops or spikes that would indicate major fragmentation events. The coma maintained its diffuse, symmetric morphology. By all appearances, the nucleus had survived perihelion intact, a testament to either structural strength or perhaps a gentle enough thermal environment that catastrophic failure didn't occur. As October 29th transitioned into October 30th and beyond, the comet began its outbound journey. The distance from the sun would now increase, solar heating would gradually diminish, and outgassing would decline. But the effects of perihelion would linger. The fresh surface exposed by sublimation, the altered dust population in the coma, the residual heat stored in the porous nucleus, all would continue influencing observable properties for weeks. For the research community, perihelion marked the climax of the observation campaign. But it wasn't the end. 3 Atlas was now heading toward its closest approach to Earth on December 19th, an event that would provide the best geometric conditions for high-resolution imaging and radar observations. The data from perihelion would inform planning for that final observing window. And already, preliminary analysis was underway. Papers began appearing on ArcSci, presenting thermal models, spectroscopic inventories, and coma morphology studies. The consensus was solidifying. 3A Atlas behaved like a comet, albeit one with unusual chemistry. The Sewell-rich, pre-perihelion state had given way to a more water-dominated, post-perihelion phase, suggesting compositional stratification. Perhaps a surface mantle, processed by radiation, overlaying a more pristine, volatile-rich interior. This layered structure model gained support from multiple lines of evidence. It explained the early carbon-rich spectra and the shift toward water at perihelion. It fit the polarimetric findings, which showed dust properties changing as fresh material emerged. And it aligned with theoretical predictions for how interstellar objects should evolve during billion-year journeys through space. Their surfaces baked and irradiated, while their cores remained frozen and unchanged. As the sun's direct caress faded and 3A Atlas moved back into the cold, the comet carried with it the marks of that brief, intense encounter. Its tail streaming behind, its coma glowing faintly in reflected sunlight, it continued on a trajectory that would carry it past Earth one last time, before accelerating toward the outer solar system and, eventually, back into the vast dark between stars. For humanity, watching from our small, warm world, the perihelion passage was a reminder of the dynamic forces shaping these ancient travelers. It was also a reminder of impermanence. 3I Atlas had spent billions of years in cold stasis, only to awaken for a few brief months under our sun's light, before returning to cold silence forever. This is not science fiction. This is October 2025. Chapter 7. November 15th, 2025, Multi-Mission Tracking, a Solar System Concert. By mid-November, 3I Atlas had become the most extensively observed interstellar object in history. Over 20 separate missions, space telescopes, planetary probes, ground-based observatories spanning 6 continents, had contributed data to what was emerging as the most comprehensive study of any comet, interstellar or otherwise, ever undertaken. It was a spontaneous symphony, each instrument playing its part, together building a 3-dimensional, multi-wavelength portrait of a visitor from beyond. The coordination required to pull this off was itself noteworthy. Telescope time is precious, allocated through competitive processes months or years in advance. But 3I Atlas had triggered a wave of directors' discretionary allocations, emergency time set aside for unexpected, high-priority targets. Space agencies communicated across traditional boundaries. NASA missions shared data with ESA missions, which in turn coordinated with JAXA and Roscosmos. Amateur astronomers contributed observations through platforms like the Comet Observation Database, their backyard telescopes adding temporal coverage that no single professional facility could match. The James Webb Space Telescope conducted 3 separate observation campaigns between perihelion and mid-November, each targeting different wavelengths. The near-infrared spectra tracked the evolution of water, calm, and methane emissions. Mid-infrared photometry measured thermal emission from dust grains, revealing their temperature and size distributions. The data showed that the coma dust was dominated by particles roughly 1 micron in diameter, small enough to be efficiently accelerated by radiation pressure, but large enough to scatter visible light effectively. Hubble added ultraviolet spectroscopy, capturing emission lines from hydroxyl radicals, atomic oxygen, and carbon. The UV observations revealed fine structure in the coma, hints of asymmetry that had been invisible at longer wavelengths. Faint jets, perhaps 3 or 4 of them, appeared to be emanating from the nucleus, though their exact geometry was difficult to resolve given the comet's distance and the diffraction limits of even Hubble's optics. Ground-based telescopes contributed high-cadence monitoring. The Very Large Telescope in Chile, the Keck Observatory in Hawaii, the Subaru Telescope, the Gemini Telescope, each took turns tracking 3 Atlas, night after night, building time series data on brightness, spectral features, and coma morphology. The regularity of observation allowed researchers to detect transient phenomena, brief brightenings lasting a few hours, possible mini-outbursts driven by localized venting of gas from subsurface cavities. The Atacama Large Millimeter Array, ALMA, a radio telescope array in Chile's high desert, turned its attention to 3E Atlas in early November. ALMA's high sensitivity at millimeter wavelengths allowed detection of molecules difficult to observe in optical or infrared light. The results, released on November 12, confirmed the presence of hydrogen cyanide, HCN, and methanol, CHAHO, both common in solar system comets and both indicators of complex organic chemistry. The methanol detection was particularly exciting. It suggested that water-rich ices had indeed persisted in the nucleus interior, now being released after perihelion erosion exposed them. Radio observations at longer wavelengths detected hydroxyl maser emission, a rare phenomenon, where O radicals in the coma amplify specific radio frequencies, creating intense, narrow spectral lines. This emission provided precise velocity information, revealing the expansion speed of gas in the coma, roughly 0.8 kilometers per second. That's typical for comets at 3I Atlas's distance and outgassing rate, another data point confirming the object's fundamentally cometary nature. But the radio observations also fueled speculation. On December 1st, the first reports of unusual radio signals associated with 3I Atlas appeared, but we're getting ahead of ourselves. In mid-November, the radio data were interpreted straightforwardly: natural emissions from water photodissociation products, consistent with a comet undergoing normal activity. Meanwhile, NASA's Mars orbiters, MAVEN, Mars Odyssey, and the Mars Reconnaissance Orbiter, attempted coordinated observations. From their vantage points orbiting the red planet, the comet appeared in a different geometric configuration than from Earth, allowing stereoscopic reconstruction of the coma structure. The imaging, though limited by resolution, hinted at a three-dimensional morphology more complex than a simple spherical envelope. Perhaps the coma was elongated, aligned with the Sun-comet vector, as expected from radiation-driven outgassing. Or perhaps there were density variations, clumps of dust and gas distributed non-uniformly. The spacecraft tracking 3E Atlas also included some unexpected participants. The James Webb Space Telescope's routine calibration observations, which scan known stars and fields to verify instrument performance, happened to pass through regions of sky near the comet. Those data, though not primarily intended for comet science, added valuable calibration points. Even the International Space Station got involved. Astronauts aboard the ISS, using handheld cameras equipped with telephoto lenses, attempted to photograph 3 Atlas during a pass when the comet was favorably positioned. The images weren't scientifically calibrated, but they captured public imagination. Human beings, floating in orbit, turning their gaze toward an object that had traveled light years, the two meeting in the same moment. The combined dataset was staggering. Terabytes of spectra, images, light curves, polarimetric measurements. By mid-November, over 15 papers had been submitted to journals, with dozens more in preparation. The arXiv preprint server saw near-daily uploads related to 3E Atlas. Topics ranged from detailed chemical modeling to dynamical simulations of the comet's past trajectory through the galaxy. One particularly intriguing study, led by Dr. Jane Greaves at Cardiff University, analyzed the comet's metal content. Spectroscopic lines corresponding to metallic species, sodium, iron, nickel, had appeared in optical and UV spectra throughout the post-perihelion period. Sodium is common in comets produced by the sublimation of silicate dust grains. But iron and nickel are less typical, usually present only in trace amounts. The Greaves paper used high-resolution spectroscopy to measure the abundance ratios of these metals. The surprising finding: nickel appeared to be overabundant relative to iron, a ratio not seen in solar system comets. In meteorites and asteroids, iron typically dominates nickel by a factor of 10 to 20. Here, the ratio was closer to parity. This abundance anomaly suggested that the nucleus contained metal grains with an unusual composition, perhaps formed in a supernova ejecta environment, where nuclear reactions produced nickel-56, which decays to iron-56 over short timescales. But if decays to iron-56 over short timescales, incorporated quickly into solid grains, might leave nickel-rich inclusions. Alternatively, the metals could have been concentrated through some unknown process in the protoplanetary disk of 3I Atlas's home system. The implications were speculative, but tantalizing. Metal-rich comets might be capable of fostering prebiotic chemistry through catalytic reactions on grain surfaces. They might also provide unusual resources for future space industries, if humanity ever developed the capability to harvest interstellar objects. But those thoughts remained firmly in the realm of imagination. The immediate scientific value was simply the expansion of known cometary diversity. Another study focused on the comet's trajectory reconstruction. By integrating the orbit backward through time, accounting for gravitational perturbations from known stars, researchers attempted to identify 3 Atlas's home system. The analysis, led by Dr. Corin Baylor-Jones at the Max Planck Institute, used data from the Gaia Space Telescope, which has measured the positions and velocities of over 1 billion stars in our galaxy. The results were frustratingly ambiguous. The comet's trajectory, traced backward for several million years, passed within a few light years of over 30 different stellar systems. Without more precise velocity measurements, difficult to obtain given the comet's distance and faintness, it was impossible to pinpoint a single origin. The best candidates were a handful of Sun-like stars in the Orion Cygnus arm of the Milky Way, roughly 500 to 1,000 light-years from Earth. But even that was uncertain. One of those candidate stars, catalogued as HD 197018, was a G-type star slightly older than the Sun, known to have a debris disk, evidence of planetary system formation. If 3 Atlas originated there, it had been traveling for roughly 1 million years to reach us. Ejected perhaps by gravitational perturbations from an unseen planet during the chaotic early phase of system assembly. It was a plausible story, one of many possible stories, forever unprovable without a direct sample return mission. As mid-November transitioned into late November, the observational focus began shifting. The comet was now outbound, moving away from the Sun but approaching Earth geometrically. The closest pass to Earth, scheduled for December 19th, was less than 5 weeks away. Radar observations were planned. If the comet came close enough, high-power planetary radar systems like the Arecibo Observatory's successor in Puerto Rico could bounce radio waves off the nucleus, obtaining direct measurements of size, shape, and rotation. But there were concerns. Funding for planetary radar had always been precarious, and budget cuts in 2024 had reduced operational capacity. Whether the facilities would be available and staffed for the critical December window was uncertain. Letters from the scientific community to funding agencies emphasized the unique opportunity. This might be the only chance to radar image an interstellar comet in our lifetimes. The multi-mission tracking effort also highlighted the growing capabilities of international collaboration. Data sharing agreements that had taken years to negotiate in previous decades were now streamlined. Real-time coordination occurred through online platforms, with researchers across time zones handing off observing responsibilities like a relay race. The comet became a testbed for a mode of operation that would be essential for future endeavors, tracking fast-moving transient objects that don't wait for bureaucratic processes. By November 15th, the three-dimensional model of 3 Atlas's coma was the most detailed ever constructed for any comet. It showed a coma extending over 300,000 kilometers, with embedded structure, shells or layers, possibly corresponding to discrete outgassing events or rotational modulation. The dust tail stretched back along the comet's orbital path, its curvature precisely matching models of radiation pressure and solar wind interaction. The ion tail flickered and waved, responding to variations in solar wind, density, and magnetic field strength. And within all that data, the nucleus itself remained a mystery, a faint point source, unresolved even by the sharpest images. Estimates of its size ranged from 3 to 7 kilometers, depending on assumptions about reflectivity. Its rotation period, if it had a simple rotation, was unknown. The light curve remained too irregular. Its shape could only be guessed. But the coma, the atmosphere and tail that the nucleus created, was no longer a mystery. It was mapped, measured, modeled. It was a portrait of cometary activity in exquisite detail, a validation of ground-based and space-based observation capabilities, and a testament to what humanity can achieve when focused on a single, compelling target. The concert was ongoing, each instrument still contributing its voice. And the crescendo, the moment when 3 Atlas would pass nearest to Earth and offer its clearest view, was still ahead. This is not science fiction. This is November 2025. Chapter 8. Early December 2525. The Heartbeat Controversy. In the first week of December, a preprint paper appeared on Archive that ignited controversy. The lead author was Professor Abraham Loeb, director of the Institute for Theory and Computation at Harvard. The paper's central claim, photometric data from 3 Atlas, showed a periodic signal, approximately 16.6 hours, that could not be easily explained by simple rotation or random outgassing fluctuations. Loeb's team argued that this heartbeat signal might indicate repetitive, localized jetting, or more provocatively, could hint at some form of propulsion. The paper was careful, hedged with caveats. It acknowledged that natural mechanisms, uneven surface heating, complex rotational states, could in principle produce periodic light variations. But it also noted that the precise regularity of the 16.16-hour cycle was unusual. Most tumbling bodies or irregularly shaped nuclei produce light curves with multiple overlapping periods, creating messy, quasi-periodic patterns. 3 Atlas's signal, as analyzed by the Loeb team using Fourier techniques on 6 weeks of photometric data, showed a dominant peak at 16.6 hours with surprising clarity. The paper stopped short of claiming artificial origin, but it did pose the question explicitly. Given the interstellar nature of this object and its chemical anomalies, should we consider the possibility that the periodic signal reflects directed activity? The phrasing was cautious, framed as a question rather than an assertion, but it was enough. The response was immediate and polarized. Mainstream cometary scientists pushed back hard. Dr. G. Matthew Knight, reached for comment by Science magazine, stated bluntly, a 16-hour period is well within the range of cometary rotation periods. There's nothing here that requires exotic explanations. Periodic brightness variations are expected. This feels like we're looking for aliens, where we should be seeing comets. Dr. Michele Bannister added, complex rotation, precession, or active regions firing in regular patterns. These are all well-documented phenomena. The Loeb paper cherry-picks a time series and applies signal processing to find periodicity. If you look hard enough, you can find patterns in noise. We need more data, longer baselines, independent confirmation before making extraordinary claims. But the paper had supporters, or at least those willing to entertain the hypothesis. Dr. Gregory Laughlin, a dynamicist at Yale who has studied unusual solar system objects, commented, I don't think it's likely that 3 Atlas is artificial. But I also don't think the question is unreasonable. We've only detected 3 interstellar objects ever. Our sample size is pathetic. Claiming certainty about what's normal or abnormal is premature. The data should drive the conclusions, not our preconceptions. The public, inevitably, latched onto the more sensational interpretation. Headlines ranged from cautious, scientists debate unusual signal from interstellar comet, to breathless, is 3 Atlas an alien probe? Social media discussions exploded. Some users dissected the paper's figures, attempting their own Fourier analysis. Others dismissed it as attention-seeking by a researcher known for provocative hypotheses. Loeb himself had a history. His previous work on Oumuamua where he suggested the object's unusual acceleration might indicate a light sail, had been controversial. Many scientists felt he had overstepped, using speculative ideas to generate media attention at the expense of scientific rigor. Others saw him as a valuable gadfly, someone willing to ask uncomfortable questions and push boundaries. The heartbeat claim fit that pattern. It was provocative, it generated discussion, and it sat on the knife edge between legitimate inquiry and sensationalism. Whether it represented good science or bad depended largely on one's perspective about the role of speculation in the scientific process. Independent reanalysis began almost immediately. Multiple research groups downloaded the public photometric data and ran their own period-finding algorithms. The results were mixed. Some confirmed the presence of a signal near 16 hours, others found multiple weaker periods. Still others argued that the signal was an artifact of data gaps or systematic errors in the photometric pipeline. One detailed critique, posted to Arxiv on December 4th, by Dr. Rosita Kokotanakova at ESO, pointed out that the observing cadence, when and how often observations were taken, had gaps that could introduce spurious periodicities. Specifically, many observatories had weather-related interruptions, and the resulting time series had unevenly spaced data points. Fourier analysis of such data is notoriously tricky, prone to aliasing effects where false peaks appear at regular intervals. Kokotanakova's paper reprocessed the data using Lomskargel periodograms, a technique designed for unevenly sampled data, and found that the 16.16-hour peak weakened significantly when proper statistical tests were applied. The signal is marginally significant at best, the paper concluded. More likely, it's a combination of the true rotation period and observational sampling effects. Yet even this rebuttal didn't entirely kill the discussion. Loeb's team responded with a follow-up note, arguing that their analysis accounted for the sampling issues and that the periodicity remained robust. They also highlighted that subsequent observations in late November and early December continued to show the same period, suggesting it wasn't purely an artifact. The debate, in many ways, exemplified a deeper tension within the astronomical community. How much speculation is healthy? Science advances through a balance of conservatism, requiring strong evidence before accepting new ideas, and openness to the unexpected. Lean too far toward conservatism, and you risk missing genuine anomalies. Lean too far toward openness, and you drown in noise and false positives. For 3I Atlas, the heartbeat controversy was a microcosm of that balance. The object was undeniably unusual in its chemistry and trajectory. Whether its photometric behavior added to that unusualness or simply reflected the complexities of complementary dynamics was a question that hinged on interpretation, on statistical thresholds, on willingness to entertain low-probability scenarios. The controversy also had practical consequences. It drove additional observations. Researchers who might have moved on to other targets instead scheduled more telescope time, determined to either confirm or refute the periodicity. High-cadence photometry, observations every few minutes rather than every few hours, was attempted during a clear sky window in early December. If the 16.6-hour period was real, continuous monitoring should reveal the detailed shape of the light curve, potentially distinguishing between rotation and pulsed jetting. Those observations, when they came, showed variability, but still no clear, unambiguous periodicity. The light curve fluctuated, sometimes brightening, sometimes dimming, but the pattern was irregular. Some cycles seemed to match the 16-hour period, others didn't. The data were consistent with a tumbling nucleus, or with irregular outgassing, or possibly with a semi-regular pattern masked by stochastic activity. In short, inconclusive. But inconclusiveness doesn't make for satisfying narratives. The public wanted answers. Is it a comet? Or is it something more? Scientists, bound by the rigor of their methods, could only say, probably a comet, but we can't rule out complexities we don't yet understand. And amid the uncertainty, Loeb's broader point, that interstellar objects deserved careful scrutiny for any signs of non-natural origin, found some traction. Not because the evidence was compelling, but because the cost of dismissing a genuine signal, should one exist, was immense. If even a 1 in 1,000 chance existed that an interstellar object was artificial, the argument went, then shouldn't we apply the most rigorous tests possible? Most scientists countered, "Of course we should test thoroughly, but we should also not lower our standards of evidence to chase every speculative hypothesis. The burden of proof lies with the extraordinary claim. Until the periodicity was confirmed beyond doubt, and until natural explanations were exhaustively ruled out, the default interpretation, 3 Atlas as a natural comet, should stand." By mid-December, the controversy had faded from headlines, though it continued percolating through academic discussions. The heartbeat remained a footnote, an intriguing, unresolved detail in the broader story of 3I Atlas. Future observations, perhaps from the next interstellar visitor, might shed light on whether such signals are common or rare, artifactual or real. But for now, in early December 2025, the question hung in the air, unanswered. And 3I Atlas continued its journey, indifferent to the debates swirling around its nature. Chapter 9. December 1st, 2025, Radio emissions, not aliens, but water chemistry. On December 1st, a press release from the National Radio Astronomy Observatory announced a significant detection. For the first time, radio telescopes had observed emissions from an interstellar comet. The signal came from the Very Large Array in New Mexico, operating at a frequency of 18 centimeters, the wavelength where hydroxyl radicals, O, emit characteristic lines. The detection was historic. No previous interstellar object had been observed in radio wavelengths. Oumuamua had been too faint and far, its coma, if it had one, undetectable. Borisov had been observed, attempts made, but the signals were below detection thresholds. 3A Atlas, brighter and more active, finally provided the necessary flux. Hydroxyl radicals are a direct product of water photodissociation. When ultraviolet light from the sun hits water molecules in the coma, it breaks the HEO bonds, producing O and hydrogen atoms. The O radicals, in turn, absorb and re-emit radio photons at specific frequencies. By measuring the intensity and profile of these emission lines, astronomers can infer the water production rate and the physical conditions, temperature, density, velocity, in the coma. The Vela observations indicated a water production rate of approximately 200 kilograms per second at the time of observation, consistent with estimates from optical and infrared spectroscopy. The emission line was Doppler broadened, indicating gas expanding at roughly 1 kilometer per second, again, typical for cometary activity. In other words, completely normal, natural, exactly what a comet should produce. The press release emphasized this. The radio emissions confirm that 3E Atlas is an active comet undergoing standard water-driven outgassing, it stated. The signals are consistent with natural processes and provide no evidence of artificial transmission. That final sentence was pointed. It was a direct response to the sensationalism surrounding the heartbeat controversy, and more broadly, to lingering speculation that interstellar objects might be probes or artifacts. The radio observations, at least, were unambiguous. This was water chemistry, textbook cometary behavior. Yet, the detection was more than just a confirmation of the obvious. It was a proof of concept. If 3I Atlas could be detected in radio wavelengths, then future interstellar visitors, even fainter ones, might also be accessible to radio astronomy. This opened new avenues for study. Radio observations can penetrate through dust and gas that obscure optical and infrared light, providing a clearer view of the inner coma near the nucleus. They can also probe molecules like ammonia, formaldehyde, and methanol, which are difficult to detect at other wavelengths. The follow-up observations, scheduled throughout December, aim to map the spatial distribution of O emission across the coma. By comparing emission from different regions, researchers could infer whether outgassing was uniform or localized. If jets were present, they should produce asymmetries in the radio map, bright spots where gas was being freshly released. Preliminary maps released on December 5th showed a roughly spherical O envelope consistent with the diffuse, symmetric coma seen in optical images. No obvious jets. This didn't rule out their existence. Jets could be present but weak, or oriented in ways that created symmetry when projected onto the sky. But it suggested that if jets existed, they weren't dominant. The radio data also allowed precise velocity measurements. The Doppler shift of the emission line revealed the expansion speed of gas in the coma, which in turn depends on the temperature and molecular weight of the gas. The measured expansion speed, around 0.9 kilometers per second, matched theoretical predictions for a coma dominated by water vapor and cohow at a temperature around 100 to 150 Kelvin. Another consistency check passed. But there was one subtle anomaly. The emission line profile wasn't perfectly Gaussian. It had slight asymmetries, with one wing of the line slightly stronger than the other. This could indicate that the coma wasn't perfectly symmetric after all, that there was some preferred direction of outgassing. Or it could be an instrumental artifact, or the result of the comet's orbital motion combined with complex gas dynamics. Interpreting such subtleties required detailed modeling. A team at the Netherlands Institute for Radio Astronomy, Astron, constructed three-dimensional simulations of gas flow in a cometary coma, accounting for solar radiation pressure, photodissociation rates, and the comet's rotation. By comparing the simulated emission profiles to the observed data, they attempted to constrain the nucleus rotation axis and the distribution of active regions. The modeling was computationally intensive, and results wouldn't be available until mid-December. But the effort underscored the scientific value of the radio detection. It wasn't just a checkbox, yes, always present, but a rich data set that could reveal the comet's internal dynamics. The public reaction to the December 1st announcement was more muted than previous revelations. Water chemistry wasn't sexy. Hydroxyl radicals didn't capture imaginations the way mysterious heartbeat signals did. And the clear statement that the emissions were natural dampened speculative excitement. But within the research community, the radio detection was celebrated. It represented technical achievement, detecting faint signals from a small distant object. It validated the investment in radio astronomy infrastructure. And it provided a template for future observations of transient phenomena, how to coordinate multi-facility campaigns, how to process and interpret radio data in near real time, how to integrate radio results with optical and infrared findings. The hydroxyl emission also allowed a consistency check on the comet's total volatile budget. By integrating water production over time, researchers estimated that 3E Atlas had lost roughly 100 million kilograms of water since perihelion, about 100,000 metric. For a nucleus several kilometers across, assuming typical cometary density around 500 kilograms per cubic meter, the total mass was on the order of 10 to 100 billion kilograms. The water loss represented a fraction of a percent, negligible in terms of total mass, but significant in terms of surface erosion. That erosion, if it continued, could eventually expose entirely different layers of the nucleus. Comets are thought to be layered, or at least heterogeneous, with different regions reflecting different formation or evolutionary histories. Continued monitoring of the radio emissions over the coming weeks might reveal changes in composition as sublimation penetrated deeper into the nucleus. By December 5th, follow-up radio observations had begun incorporating other molecular transitions. Formaldehyde, targeted, though initial attempts came up empty. Either the molecule was present below detection limits, or it simply wasn't abundant. Methanol, KEO, was tentatively detected, though the signal was weak and required confirmation. Each detection, or non-detection, added a piece to the chemical puzzle. The overall picture emerging was of a comet broadly similar in molecular content to solar system comets, but with quantitative differences. Less water relative to carbon dioxide, more CO, possibly more methanol. These differences, while significant, were differences of degree rather than kind. 3 Atlas wasn't made of exotic materials or emitting inexplicable signals. It was a comet, shaped by the same physics and chemistry that govern all comets, but with a compositional twist reflecting its foreign origin. The December 1st radio detection became a turning point in the narrative. Before that announcement, the conversation had been colored by uncertainty, by speculation about unusual behavior and possible artificial origin. After December 1st, the tone shifted toward acceptance. The comet was natural. The radio emissions proved it. Yes, Mysteries remained: unusual chemistry, irregular photometry. But those were puzzles within the framework of natural processes, not hints of something beyond. And yet, the sense of wonder didn't diminish. Because even a natural interstellar comet carried profound implications. It was a messenger from another star, a physical sample of another planetary system, a traveler through the galactic medium. No. The fact that it was just a comet didn't make it any less extraordinary. As December progressed, the focus turned toward the final act. The closest approach to Earth on December 19th. The radio telescopes would continue their watch, but the spotlight was shifting to optical and radar observations, the last chance to see 3I Atlas in detail before it faded forever. Chapter 10. December 5th, 2025. Composition complexity, metals, carbonaceous chondrites, and possible aqueous history. On December 5th, a paper appeared in Nature Astronomy that synthesized months of spectroscopic and photometric data into a comprehensive compositional model. The lead author, Dr. Alessandro Springmann at the Planetary Science Institute, proposed a provocative hypothesis. 3I Atlas might resemble carbonaceous chondrite meteorites, a class of primitive carbon-rich rocks found on Earth that are believed to represent some of the earliest solid material in the solar system. The paper's key argument rested on the metal abundances. Spectra from November and early December had revealed not only sodium, but also iron, nickel, and even trace amounts of cobalt and chromium. The ratios of these metals, when plotted and compared to meteorite samples, clustered near the region occupied by carbonaceous chondrites, specifically the Ci and Cm subgroups. Carbonaceous chondrites are unusual. They contain significant amounts of water, up to 10% by mass, locked in hydrated minerals, and complex organic molecules, including amino acids. They're thought to have formed in the outer reaches of the early solar system, where temperatures were cool enough for water and organic compounds to condense. And crucially, many of them show evidence of aqueous alteration, chemical changes caused by liquid water circulating through the rock. Despite never having been on a planet with surface oceans. How does water circulate in a rock floating in space? Through internal heating. Radioactive decay of short-lived isotopes, like aluminum-26, can generate enough warmth to melt ice embedded in the rock, creating transient pockets of liquid water that percolate through fractures and pores. Over millions of years, this water alters minerals, creating clays and carbonates, the same minerals found in carbonaceous chondrites. The Springmann paper suggested that 3I Atlas might have undergone a similar process billions of years ago. If the nucleus contained metal grains and water ice in close proximity, and if the object was large enough to retain heat from radioactive decay, then liquid water could have existed inside the comet for perhaps 1 million years after its formation. That water could have driven chemical reactions, mineral alterations, organic synthesis, possibly even prebiotic chemistry. This scenario was speculative, but it fit the data. The metal-rich spectra indicated that the nucleus had substantial solid material mixed with ices. The carbon dioxide and organic molecules implied a chemically reducing environment, one where carbon chemistry could flourish. And the presence of water vapor, even if currently subdued, suggested that water had always been part of the comet's composition, not just a surface frost. The paper explored the implications using thermochemical models. If metal grains, iron-nickel alloys, sulfides, were embedded in ice and heated, they could catalyze Fischer-Tropsch reactions, chemical processes that convert carbon monoxide and hydrogen into more complex hydrocarbons and alcohols. These reactions occur naturally in some terrestrial environments, catalyzed by iron minerals, and they're thought to have played a role in prebiotic chemistry on early Earth. Could the same processes occur in a comet? If the nucleus interior reached temperatures above 250 Kelvin, warm enough for liquid water, then yes, possibly. The products of such reactions, methane, ethane, methanol, formic acid, would be trapped in the ice matrix, only to be released now, billions of years later, as the comet outgassed near the sun. The paper didn't claim direct evidence for a Fischer-Tropsch chemistry in 3I Atlas. The spectroscopic data weren't detailed enough. But it proposed this as a testable hypothesis. If future observations detected unexpected hydrocarbons or organic molecules not typically seen in comets, it could indicate past internal aqueous chemistry. The carbonaceous chondrite analogy also helped explain the Ka richness. Some carbonaceous chondrites contain carbonate minerals, essentially fossilized carbon dioxide locked into rock by reactions with water. If 3I Atlas had undergone aqueous alteration, carbonates could have formed, later releasing Ka when the comet was heated by the sun. This would supplement primordial Ka ice, boosting the abundance beyond what formation conditions alone would predict. Dr. Bethany Eilman, a planetary geologist at Caltech, commented on the paper. This is a really creative interpretation. It ties together the metal detections, the kaon, and the hints of complex organics into a coherent story. It's also testable. We can look for specific molecular signatures that would confirm or refute the aqueous alteration hypothesis. I hope future interstellar comets give us the opportunity to do that. But the hypothesis faced skepticism. Dr. Paul Weissman, a veteran comet researcher, pointed out that aqueous alteration requires sustained heat over long timescales. For a comet nucleus only a few kilometers across, heat loss would be rapid. Unless the object was originally much larger, tens of kilometers, and later fragmented, it's difficult to maintain internal liquid water long enough for significant chemistry. Carbonaceous chondrites come from asteroids, which are larger and can retain heat, Weissman said. A comet nucleus is small, porous, and thermally inefficient. I'm not convinced the conditions were right for aqueous processes. The metal detections could just reflect the elemental composition of the protoplanetary dust without requiring liquid water. The debate highlighted a central challenge in studying interstellar objects. Without samples, we can't perform the detailed lab analysis that resolves these questions for meteorites. On Earth, scientists cut open carbonaceous chondrites, examine their minerals under microscopes, measure isotopic ratios to parts per billion precision. For 3I Atlas, we have spectra, integrated light from a body unresolved even by our best telescopes. The ambiguity is immense. Still, the carbonaceous chondrite hypothesis enriched the conversation. It connected cometary science to meteorite studies, two fields that often operate in parallel but don't always intersect. It also expanded the potential role of comets in delivering prebiotically relevant molecules to planets. If comets like 3 Atlas carry not just simple ices but complex organics synthesized through internal chemistry, they become even more interesting as vectors for life's building blocks. The paper's final section discussed implications for exoplanetary science. If interstellar comets carry organic-rich, water-altered material, then planets in other star systems might receive similar bombardments during their formation. The idea of panspermia, life spreading between star systems via comets or meteorites, has long been speculative, but objects like 3I Atlas made it seem slightly less far-fetched. Not panspermia of living organisms, which would struggle to survive the radiation and cold of interstellar space, but panspermia of chemistry, organic molecules, and water delivered to young planets, seeding them with the ingredients for life. As December 5th transitioned into the days that followed, the Springman paper became one of the most cited references in the 3I Atlas literature. It didn't provide definitive answers, no single paper could, but it framed questions in ways that guided future observations. If methanol or formic acid was detected, that would support the Fischer-Tropsch hypothesis. If carbonate minerals could be inferred from infrared absorption features, that would strengthen the aqueous alteration scenario. The comet, indifferent to these debates, continued on its trajectory. Its coma glowed faintly, its dust tail stretched across millions of kilometers, its nucleus, perhaps metal-rich, perhaps carbonaceous, perhaps both, remained hidden within the haze. The closest approach to Earth was 2 weeks away, and the anticipation was building. Chapter 11, December 10th, 2025. Hidden dynamics, jets, antitails, and tail morphology shifts. By December 10th, something unexpected began appearing in high-resolution images of 3I Atlas, an antitail. In cometary parlance, an anti-tail is a narrow, spike-like feature pointing toward the sun, seemingly defying the physics that pushes normal tails away from the sun. It's not a real reversal of physics, of course, but a projection effect. When Earth passes through the comet's orbital plane, we see the dust tail edge on, and the perspective creates the illusion of a tail pointing sunward. Anti-tails are rare, but not unheard of. They require specific geometric alignment. The comet, Earth, and the orbital plane must all line up just right. For 3I, Atlas, that alignment occurred in early December, and several amateur astronomers, scanning the skies with sensitive cameras, captured the first images of the feature. The anti-tail was faint, visible only in processed images where the coma's brightness was subtracted to reveal the faint tail structure. But its presence confirmed that the dust tail had a planar structure, grains concentrated in the orbital plane, forming a thin sheet. This was expected from theory. As dust is released from the nucleus, it inherits the comet's orbital motion, spreading out in a flat disk aligned with the orbit. When seen edge-on, that disk appears as a narrow spike. But more intriguing was the discovery, on December 12th, of what appeared to be sunward jets, bright streamers in the coma pointing directly toward the sun. Normally, jets are driven by sublimation and point away from the hottest regions of the nucleus, which are usually the sunward side. Sunward jets shouldn't exist unless something unusual was happening. The initial images, captured by the TRAPPIST-South robotic telescope in Chile, showed two distinct jets emanating from the nucleus region, one pointing roughly toward the sun, the other pointing perpendicular to the sun-comet line. The sunward jet was fainter but unmistakable in processed images. Dr. Colin Snodgrass, a cometary scientist at the University of Edinburgh, proposed an explanation. The sunward jet might not be a jet at all, but rather a shadow effect. If the comet nucleus was irregularly shaped, or if there was a large boulder or fragment near the nucleus, it could cast a shadow in the dusty coma. From certain angles, this shadow would appear as a dark lane, and the illuminated regions on either side might look like a bright jet pointing sunward. Alternatively, the sunward feature could be a real jet, but one driven by thermal lag. Cometary nuclei don't heat uniformly. The subsurface layers take time to warm up after sunrise on the comet's surface. If outgassing is driven by subsurface heat, reaching buried ices hours after sunrise, the active region could be on the evening side of the nucleus, facing toward the sun in the sky, but rotationally displaced. From Earth's perspective, this would appear as a jet pointing sunward. Testing these hypotheses required detailed modeling of the comet's rotation and thermal state. Without knowing the rotation period or axis orientation, the models were under constraint. But the presence of structured jets, real or illusory, indicated that the coma wasn't as featureless as mid-November observations had suggested. The comet was revealing complexity as it drew closer, as our viewing angle changed, and as activity levels fluctuated. The tail morphology also began showing rapid changes. On December 11th, the dust tail appeared broad and diffuse. By December 13th, it had narrowed considerably, and a secondary tail, a faint streamer at a slightly different angle, had appeared. These changes occurred over just 2 days, suggesting a discrete outgassing event or perhaps fragmentation. Fragmentation was a real possibility. Comets under thermal stress can crack and split, releasing clouds of dust and gas in sudden bursts. If 3A Atlas had undergone a fragmentation event, the newly released material would form a transient tail feature, visible for a few days before dissipating or merging with the main tail. Photometric monitoring around December 12th showed a brief brightening, about half a magnitude over 6 hours, followed by a gradual decline. This light curve was consistent with an outburst. Spectroscopy taken during the brightening showed enhanced CN and Ca emission, indicating that fresh, carbon-rich material had been released. Dr. Matthew Knight, analyzing the outburst data, commented, "This looks like a classic cometary outburst, sudden release of volatiles from a subsurface pocket that was breached by thermal cracking. It's not a fragmentation in the sense of the nucleus breaking apart, but rather a localized failure of the surface layers, exposing fresh ice." The outburst hypothesis was supported by follow-up imaging. In the days after December 12th, The coma showed faint shells, expanding envelopes of dust and gas, concentric rings centered on the nucleus. These shells are a common signature of discrete outgassing events, their visibility depending on the viewing geometry and the time elapsed since the event. But some researchers saw hints of more than just outbursts. Dr. Zdeněk Sekanina, a veteran dynamicist at JPL, analyzed the tail morphology shifts using archival images and noted that the changes could also be explained by a slowly fragmenting nucleus. Not a catastrophic breakup, but a gradual separation of fragments that remained loosely bound by gravity and weak cohesion. If the nucleus is a rubble pile, a collection of smaller pieces held together loosely, then thermal stresses could cause differential motion. Some pieces move slightly away from the main nucleus, creating separate zones of activity. This produces complex coma morphology and variable light curves without a full fragmentation, Sekanina explained. The rubble pile model had precedent. Several solar system comets, including 67P Churyumov-Gerasimenko, visited by the Rosetta spacecraft, are known to be contact binaries or aggregates of multiple components. If 3I Atlas had a similar structure, it would explain many of the observed oddities: irregular photometry, diffuse coma, structured jets appearing and disappearing. By mid-December, the observational picture was one of a dynamically active object, possibly structurally complex, undergoing variable outgassing as it moved through a critical thermal regime. The anti-tail, sunward jets, tail morphology shifts, outbursts, all pointed to a comet in the throes of responding to solar heating, its surface cracking, its internal ices vaporizing, its structure perhaps slowly coming apart. And yet, despite this dynamism, the nucleus remained intact. There were no reports of discrete fragments, no catastrophic disintegration. 3I Atlas was holding together, for now, even as it shed material and revealed internal complexity. The December 10th, 13th observations became some of the most visually compelling data from the entire campaign. Images showing the delicate anti-tail, the faint jets, the expanding shells. These were widely shared on social media, in press releases, and in public talks. They humanized the comet, in a sense, showing it as a dynamic, evolving entity rather than a static point of light. And they set the stage for the final week of observation. The closest approach to Earth on December 19th would offer the best spatial resolution, the highest signal-to-noise, and the last opportunity to capture the comet in detail. If fragmentation or major outbursts were going to happen, the next week was the likely window. Chapter 12. December 12, 2025, Human Stakes, the race to document the departing visitor. December 12th was more than just another day in the observational timeline. It marked the moment when the reality set in. This was ending. In 1 week, 3I Atlas would make its closest approach to Earth, and then begin accelerating away, outbound on a trajectory that would carry it beyond Pluto's orbit by mid-2026, and beyond the heliosphere, into true interstellar space within a few years. Every data point captured now was irreplaceable. Every observation that failed, due to weather, equipment malfunction, or funding gaps, was lost forever. The urgency was palpable. Observatories around the world operated on maximal schedules, allocating every clear night to 3I Atlas observations. Amateur astronomers coordinated through online forums, staggering their observations to maintain near-continuous coverage. Professional researchers, some of whom had been working on the comet for months, felt the pressure of looming finality. But pressures of another kind were also mounting. Budget constraints that had simmered in the background throughout the observation campaign now became acute. The planetary radar facilities, critical for obtaining direct measurements of the nucleus size and shape, faced operational uncertainty. The Arecibo Observatory in Puerto Rico, which had been the world's most powerful planetary radar until its catastrophic collapse in 2020, had no successor fully operational. The upgraded Goldstone radar in California was available, but its scheduling was constrained by competing demands from asteroid surveys and deep space missions. A funding request for emergency allocation to support extended Goldstone operations during the December 19th closest approach had been submitted to NASA headquarters in November. As of December 12th, approval was still pending. Without it, the radar observations would be limited to a few hours rather than the round-the-clock coverage that would maximize data quality. Dr. Lance Benner, who leads the planetary radar program at JPL, expressed frustration in a NASA town hall meeting. "We're watching a once-in-a-lifetime opportunity slip through our fingers because of budget cycles. This isn't about lack of capability. We have the dish, we have the transmitter, we have the personnel. It's about funding authorization to operate at full capacity. If we don't get approval in the next 48 hours, we lose half the observing window." The situation exemplified a broader challenge in astronomy: the mismatch between bureaucratic timescales and astronomical timescales. Planning cycles for government funding operate on fiscal years, budget reviews, allocation processes that take months. Comets, by contrast, don't wait. They arrive on their own schedules, indifferent to human administrative structures. Public advocacy emerged as a response. Social media campaigns urged space agencies to prioritize 3 Atlas observations. A petition circulated, gathering over 100,000 signatures, calling for emergency funding. Prominent scientists gave interviews highlighting the scientific value and the irreversibility of inaction. On December 14th, NASA announced that supplemental funding had been approved for extended radar operations. The decision came just 5 days before closest approach, cutting it perilously close. But it meant that the radar campaign could proceed as planned, continuous tracking from December 18th through December 21st, bouncing radio waves off the nucleus, measuring the return signal to determine size, shape, and surface properties. The radar technique is powerful but demanding. It requires precise pointing, enormous transmitter power, and sensitive receivers. The transmitted signal, traveling at the speed of light, takes minutes to reach the comet and return. The reflected signal is faint. Only a tiny fraction of the transmitted power bounces back, but it carries information encoded in time delays and Doppler shifts. From those subtleties, researchers can reconstruct a 3-dimensional image of the nucleus, resolving features as small as tens of meters. If successful, the December radar observations would be the first ever radar imaging of an interstellar object. They would definitively answer the question of nucleus size and provide the first direct evidence of shape. Is 3I Atlas elongated, like Oumuamua, spherical, fragmented? The radar would tell. But radar wasn't the only technique racing against time. High-resolution optical imaging required excellent atmospheric conditions, clear skies, minimal turbulence. Ground-based telescopes using adaptive optics could, in theory, resolve the inner coma well enough to see individual jets and perhaps even the nucleus itself. But Earth's atmosphere is fickle. A week of clouds could ruin everything. Weather forecasts became as critical as orbital integrations. Observatories in Chile's Atacama Desert, blessed with some of the clearest skies on Earth, were the primary hope. But even there, December is summer in the southern hemisphere, and afternoon clouds often roll in. Observing windows were narrow, a few hours each night, weather permitting. The human element of the campaign also surfaced in the stories of individual researchers. Dr. Emily Kramer, a planetary scientist who had been studying 3I Atlas since July, described the toll in an interview. "You're living on comet time. You sleep when the comet sets, you wake when it rises. You're checking weather forecasts, telescope schedules, data downloads. It's exhilarating and exhausting. And you know it's temporary. This will end. And you'll probably never get another chance to study something like this in your career." For amateur astronomers, the experience was similarly intense. Many had invested in new equipment, better cameras, tracking mounts, specifically to observe 3I Atlas. They spent nights in cold backyards, adjusting focus, stacking exposures, processing images to tease out faint details. And they contributed real science. Their continuous monitoring filled gaps between professional observations, capturing transient events that might otherwise have been missed. The sense of collective endeavor, professionals and amateurs, institutions across countries and continents, all focused on one target: created a unique moment in astronomy. It wasn't the first time such coordination had occurred, but it was perhaps the most globally synchronized and publicly visible. Social media platforms filled with images, light curves, spectra. The hashtag #3Atlas trended intermittently. News outlets ran features on the comet and the scientists tracking it. And yet, beneath the excitement, there was also melancholy, because every observation brought the end closer. The data were accumulating, yes, but so was the distance. By December 19th, the comet would be as close as it would ever get. After that, it would recede, dimming, fading, until even the largest telescopes could no longer detect it. Probably within weeks. Certainly within months. The finality was stark. Unlike planetary missions, which can orbit and study a target for years, or asteroids, which return predictably, 3IS was a one-time encounter. There would be no follow-up mission, no second look. What we learned in these few months was all we would ever learn, unless, improbably, the comet returned millennia from now, or unless some future civilization with far greater capabilities intercepted it in the depths of space. This temporal pressure, the awareness of irreversible loss, lent weight to every decision. Which observations to prioritize? Which hypotheses to test first? If telescope time was limited, should it go toward spectroscopy, photometry, or imaging? Every choice had opportunity costs. Dr. Michele Bannister captured the sentiment in a blog post. We're writing the definitive study of an object we'll never see again. The archive we're building, the data, the papers, the images, will be the only record. Future students will study 3E Atlas the way we study historical comets, from data collected by people long gone. That's simultaneously empowering and humbling. We're custodians of knowledge for a future we won't see. Nindaitschum. As December 12th turned into December 13th, 14th, 15th, the countdown continued. Clear skies. Good data. The comet cooperating, no catastrophic fragmentation, no sudden fading. And the anticipation building toward December 19th, the moment of closest approach, the finale. Chapter 13. December 19th, 2025. The closest approach, a grand finale. December 19th, 2025 Tardipoy. At 11:34 Universal Time, 3 Atlas reached its point of closest approach to Earth, approximately 170 million miles, or 0.91 astronomical units. Still far, nearly the distance from Earth to the Sun, but closer than it would ever be again. For a brief window, measured in hours, the geometry aligned. Earth, comet, and Sun positioned such that observations from our planet offered the highest possible resolution and signal strength. Observatories worldwide had prepared. In Chile, the Very Large Telescope and the Magellan Telescope stood ready, their mirrors trained on the faint smudge of 3I Atlas against the background stars. In Hawaii, the Keck and Subaru telescopes, perched atop Mauna Kea, waited for nightfall to begin their campaigns. In California, the Goldstone radar facility began transmitting high-power radio pulses, the signal racing across space toward the comet. Amateur astronomers, too, were poised. Thousands of backyard telescopes, from suburban driveways to remote dark sky sites, turned toward the same patch of sky. Images would be captured, processed, uploaded to shared databases. It was citizen science on a global scale, a spontaneous collaboration driven by curiosity and the knowledge that this moment was singular. The first radar echoes returned just after midnight UTC on December 19th. The Goldstone team, monitoring the return signal in real time, saw a faint spike, evidence that radio waves had indeed bounced off the nucleus and returned to Earth. The delay time confirmed the distance, and the width of the spike provided the first constraint on nucleus size, somewhere between 4 and 6 kilometers in diameter, depending on shape and orientation. Over the next 6 hours, as the radar continued transmitting and receiving, the data accumulated. Doppler shifts in the return signal encoded rotation information. The nucleus was tumbling, with at least 2 rotational components, confirming the suspicions from photometric data. The radar image, still blurry and preliminary, hinted at an irregular shape, perhaps elongated, perhaps bilobed, definitely not a simple sphere. Dr. Lance Benner, leading the radar analysis, described the emerging picture. We're seeing something that looks like a peanut or a contact binary. Two lobes touching or very close together. That's common for comets and asteroids. It suggests this body either formed through gentle collision, or it's been held together by very weak gravity and hasn't yet separated. The radar imaging continued through December 19th and into December 20th, building up resolution as multiple echoes were combined. By December 21st, a preliminary three-dimensional model emerged, a bifurcated nucleus, roughly 5.5 kilometers along its long axis, with a narrower neck connecting two larger lobes. The surface appeared relatively smooth at the scale of radar resolution. No giant boulders or sharp cliffs visible, though smaller-scale roughness couldn't be ruled out. Meanwhile, optical observations captured the coma in unprecedented detail. Adaptive optics systems, which correct for atmospheric blurring in real time, allowed ground-based telescopes to achieve resolution comparable to space-based observatories. The images revealed jets, at least 4 distinct streamers emanating from the nucleus region, their brightness varying over the course of hours. One jet, oriented roughly sunward, appeared to pulse, brightening and fading with a period close to 16 hours. This lent some support to the heartbeat periodicity claim, though skeptics noted that a single jet, modulated by rotation, would naturally produce such a signal without requiring exotic explanations. Spectroscopy during closest approach yielded the deepest, highest signal-to-noise spectra of the entire campaign. Water vapor, carbon dioxide, carbon monoxide, cyanide, hydroxyl, and now, confirmed for the first time, methanol and formaldehyde. The detection of these oxygen-bearing organics supported the hypothesis that the nucleus contained complex chemistry, possibly produced through internal aqueous processes eons ago. The James Webb Space Telescope, observing in infrared, captured thermal emission from the nucleus itself. Not just the coma. The temperature was measured at approximately 220 Kelvin, consistent with a surface partially covered in dark, absorbing material, perhaps organic tars or silicate dust. The thermal data also allowed estimation of surface thermal inertia, a measure of how quickly the surface heats and cools. The low inertia suggested a porous, fluffy surface, like freshly fallen snow, rather than solid rock. Ultraviolet spectroscopy from Hubble revealed atomic emissions. Oxygen, carbon, hydrogen. The ratios of these atoms provided clues to the photodissociation rates and the composition of parent molecules. One unexpected finding: a faint emission line from singly ionized calcium, indicating that calcium-bearing minerals were being vaporized in the coma. This was unusual, as calcium emission is more commonly associated with rocky asteroids than icy comets. It hinted again at the metal-rich nature of 3E Atlas. The multi-wavelength observations, synchronized across dozens of instruments, created a portrait far more detailed than any single facility could achieve. Infrared showed temperature and thermal properties. Optical revealed morphology and dust. UV probed atoms and ionization. Radio tracked molecules. Radar measured shape and size. Together they painted a picture of a bifurcated, metal-rich, organically complex, actively outgassing interstellar comet, a cosmic visitor shaped by processes we're only beginning to understand. As December 19th turned into December 20th, the comet began to recede. The distance increased, the signal weakened. Observatories continued collecting data, but the peak moment had passed. The grand finale was over, though the echoes would reverberate for months as researchers processed and analyzed the data. The public followed along too. Live streams from observatories broadcast the observations. NASA's social media accounts posted updates. News segments featured interviews with scientists. For a brief time, 3 Atlas captured collective attention in a way few astronomical events do. Not as spectacular as a meteor shower or solar eclipse, but as something deeper, a reminder of our place in a galaxy teeming with stories, a connection to processes and places far beyond human experience. One widely shared image, captured by an amateur astronomer in Australia, using a modest 8-inch telescope, showed the comet as a faint, diffuse glow with a delicate tail stretching across the frame. The photographer captioned it simply, "A visitor from the stars passing through. We were here to see it." That sentiment resonated. In a century where humanity faces enormous challenges, climate, conflict, inequality, the appearance of 3 Atlas offered a moment of unity. For a few months, people across divides looked up at the same object, wondered the same questions, shared the same curiosity. It didn't solve problems, but it reminded us of shared wonder. As the closest approach concluded, scientists began the long process of synthesis. The data were vast, terabytes of images, spectra, radar, echoes. Papers would take months to write, peer review would extend into 2026, but preliminary conclusions were already forming. 3I, Atlas was natural, a comet, definitively. Its chemistry was unusual, but within the bounds of known physics. Its structure, bifurcated and porous, resembled many solar system comets. Its composition, metal-rich and carbon-rich, suggested formation in an environment different from our own solar system's history, but not impossibly alien. The heartbeat periodicity remained ambiguous, likely rotational modulation, possibly with irregular components. The radio emissions were standard hydroxyl, nothing artificial. The outbursts and tail morphology shifts were consistent with cometary dynamics. In short, extraordinary, but natural. A window into another star's planetary system, a probe of interstellar chemistry, a test of our observational capabilities. But not a probe in the literal sense, not a spacecraft, not a message, just a comet, traveling through the dark. And yet, just a comet doesn't capture it. Because this comet had journeyed for millions or billions of years to reach us. Because its formation was shaped by a star we'll likely never identify. Because its chemistry tells stories about planetary systems beyond our reach. Because, for a few months, it was here, close enough to touch with our instruments, if not our hands, and then it was gone. December 19th, 2025, will be remembered as the day humanity got its best look at 3E Atlas star E. The data captured on that day, and in the surrounding week, will be studied for decades. And when the next interstellar visitor appears, whether in 5 years or 50, the lessons learned from 3I Atlas will guide our observations. This is not science fiction. This is December 2025. And the universe has given us a gift, the chance to glimpse its diversity, its vastness, its indifference, and its beauty. Chapter 14. January 2026, and beyond. Reflection, implications, and the road ahead. By early January 2026, 3I Atlas had faded below magnitude 13, too faint for all but the largest telescopes to track reliably. Observing campaigns wound down. Data processing ramped up. The comet, now racing outward past Mars's orbit, was slipping back into the darkness from which it came. Within a year, it would cross Jupiter's orbit. Within a decade, it would be beyond Neptune, in the realm of the Kuiper Belt. And within a century, it would exit the sun's gravitational influence entirely, returning to the interstellar medium as an anonymous traveler among trillions. But the story 3A Atlas left behind was far from over. In universities, research institutes, and space agencies worldwide, scientists sifted through the accumulated data. The synthesis was massive, over 50 papers submitted to journals by mid-January, with more in preparation. Conferences planned special sessions on interstellar objects. Graduate students began dissertations analyzing specific aspects: the Ku-rich coma, the radar shape model, the metal abundances, the outburst dynamics. Consensus began to solidify. 3. Atlas was, with extremely high confidence, a natural object, an interstellar comet shaped by ordinary, if poorly understood, processes. The evidence was overwhelming. The spectroscopic signatures matched known molecular emissions. The outgassing followed predictable thermal models. The radar shape resembled other cometary nuclei. The dynamical behavior obeyed Newtonian mechanics without standard non-gravitational forces from sublimation. The exotic hypotheses, artificial origin, directed propulsion, found no support in the data. The heartbeat periodicity, when subjected to rigorous statistical analysis, appeared to be either a marginal detection of rotational modulation or, more likely, an artifact of observational sampling combined with irregular activity. The radio emissions were standard hydroxyl and had nothing to do with communication. The unusual chemistry, while striking, was explicable within the framework of natural cometary evolution and interstellar radiation processing. Yet the comet's naturalness didn't diminish its scientific importance. If anything, the accumulated data expanded our understanding of how diverse natural processes can be. 3. Atlas challenged simplistic models of cometary composition, forced reconsideration of how radiation processing alters surfaces over geological time, and provided the first detailed look at volatiles from another star system. The C/Tahoe ratio, among the highest ever measured, became a benchmark. It demonstrated that interstellar comets could be chemically inverted relative to solar system norms. This had implications for planet formation theory. If comets deliver volatiles to young rocky planets, then the chemical inventory of those deliveries varies by star system. Some worlds might receive water-rich bombardments, fostering oceans and temperate climates. Others might receive calm-rich impacts, leading to thick greenhouse atmospheres and runaway warming. The metal-rich composition, iron, nickel, cobalt, suggested that the protoplanetary disk from which 3I Atlas formed had higher metallicity in our Sun's natal environment. This tied into broader studies of galactic chemical evolution. Stars formed from gas, enriched by earlier supernova explosions, carry higher metal content, and their planetary systems reflect that enrichment. 3 Atlas, if it indeed came from a metal-rich star, was a physical sample of that enrichment. A meteorite not from our solar system, but from another, delivered to our doorstep by chance. The radar shape model, bifurcated, contact binary, added to the growing understanding that many small bodies, whether comets or asteroids, are loosely bound aggregates rather than monolithic rocks. This has implications for planetary defense. If a threatening asteroid were discovered on a collision course with Earth, understanding its internal structure would be critical for deflection strategies. The 3 Atlas, though never a threat, provided data relevant to that future challenge. The bifurcated shape also sparked discussions about formation mechanisms. Did 3A Atlas form as two separate bodies that gently collided? Or did it form as a single, larger body that partially fragmented? The radar data couldn't answer definitively, but the existence of a neck connecting the lobes suggested low-velocity collision or gravitational reaccumulation after a disruption event. Either way, it pointed to a violent but non-catastrophic history. The outburst behavior, documented on December 12th, and possibly other times, demonstrated that 3 Atlas's activity was not just a smooth response to solar heating, but punctuated by discrete events, sudden releases of volatiles from subsurface pockets. This is common in solar system comets and results from thermal waves penetrating into porous material, reaching icy layers that suddenly vaporize. The similarity suggested that despite their different origins, comets across the galaxy share fundamental physical properties: porous structure, layered composition, volatile-driven activity. But beyond the specifics of 3I Atlas, the observation campaign itself became a case study. The coordination across missions, the integration of professional and amateur data, the rapid response allocation of telescope time, all worked more or less. Challenges remained. Funding delays nearly derailed radar observations, weather gaps left holes in coverage, and some instruments simply weren't available or capable. But the overall success demonstrated that when the astronomical community focuses on a target, impressive results follow. This experience informed planning for future interstellar visitors. Proposals began circulating for a dedicated rapid response network, a set of small, agile spacecraft parked in solar orbit, capable of quick trajectory adjustments to intercept passing objects. Funding was uncertain, but the concept gained political traction. A coalition of space agencies, NASA, ESA, JAXA, and others, initiated preliminary discussions on an interstellar object observatory mission. The public interest in 3I Atlas also left a mark. Science communicators noted a measurable uptick in engagement with planetary science topics. Enrollment in astronomy courses ticked upward in early 2026. Documentaries were commissioned, books planned. The comet became a cultural reference point, a symbol of the unknown and the knowable. But there was also reflection on what wasn't learned. Despite months of observation and terabytes of data, fundamental questions remained unanswered. The exact origin star? Unknown. The age of the nucleus? Uncertain. Estimates range from a few hundred million to several billion years. The interior composition? Inaccessible, inferred only from surface activity. The full chemical inventory? Limited by the sensitivity and wavelength coverage of available instruments. These gaps underscored the limits of remote sensing. Spectra and images provide immense information, but they can't replace touch. A sample return mission, landing on an interstellar comet, drilling into its nucleus, bringing material back to Earth, would answer questions that spectra never could. Isotopic ratios, for instance, which fingerprint the nuclear processes in a comet's parent star, require mass spectrometry at parts per thousand precision, impossible from millions of kilometers away. Such a mission remains, for now, science fiction. The technical challenges, matching velocities with a hyperbolic object, performing rendezvous operations at high speed, surviving the round trip, are immense. But the vision is there, articulated in papers and conference talks. Perhaps by mid-century, humanity will have the capability. Perhaps 3I Atlas, by demonstrating what can be learned from observation alone, will spur the development of that capability. As January turned into February, the frequency of new 3I Atlas papers slowed. The comet, now faint and distant, was no longer generating new observations, only deeper analysis of existing data. Researchers turned to other projects, though many kept 3I Atlas datasets open, ready to revisit if new questions or techniques emerged. And there was a broader context. 3I Atlas was the third known interstellar object, but it wouldn't be the last. Statistical models, updated with the discovery rate, predicted that 1 or 2 interstellar visitors pass through the inner solar system every year. Most too faint to detect, some bright enough to find if we're watching carefully. Improvements in survey telescopes, particularly the Vera C. Rubin Observatory, scheduled to begin operations in 2025, promise to increase detection rates dramatically. By the 2030s, interstellar objects might be routine discoveries, each adding to the sample size, each constraining models of planetary system formation and evolution. 3I Atlas would then be remembered as a pioneer case, the first interstellar comet studied in comprehensive detail, the object that established observational and analytical protocols for those that followed. Its legacy would lie not just in the specific findings about COA-rich comas or bifurcated nuclei, but in the framework it created for understanding interstellar visitors as a population. There was also a poetic dimension, one that scientists acknowledged, even if it lay outside formal papers. 3I Atlas came from somewhere. A star, a planetary system, perhaps a disk teeming with planetesimals like our Kuiper belt. That star, wherever it is orbiting the galactic center, carrying with it planets, if they exist, histories, processes. 3I Atlas is a piece of that distant place, ejected by gravitational slingshot, wandering the galaxy for eons, and by sheer chance passing close enough to our sun to be seen. The improbability is staggering. Space is vast. Stars are separated by light years. The chance that a body ejected from another system would cross our path, at a time when we had the technology to detect and study it, is infinitesimal. And yet, it happened. And it will happen again. And each time, we get a glimpse, a cosmic message, though not an intentional one, of the diversity and richness of the galaxy. Dr. Michelle Bannister, reflecting on the campaign in a public lecture, said, "We often talk about searching for life in the universe, sending signals, listening for replies. But the universe is already sending us signals, not in radio waves, but in physical objects. Comets, asteroids, interstellar visitors. They're messengers, carrying information about places we can't visit, processes we can't observe directly. Our job is to learn to read those messages. 3I Atlas taught us how to read a little better. Well, then, well, it had, and as 2026 progressed, 3A Atlas became history. The comet itself, indifferent to human attention, continued its silent journey. The research it sparked became part of the scientific literature, cited, debated, built upon. And the community of astronomers, having shared this experience, looked ahead to the next visitor, the next mystery, the next fleeting connection to the cosmos beyond. In a sense, the story of 3I Atlas is the story of astronomy itself. Distant things, barely visible, studied with patience and ingenuity, revealing truths about the universe and our place in it. It's a story of technology, telescopes, spectrographs, radar systems, but also of human curiosity, collaboration, and the desire to understand. And it's a story that continues, because the galaxy is vast, and we are small, but we are watching. And the universe, in its indifference, keeps sending us travelers from afar. We need only look up and listen and learn. This is not science fiction. This is our reality. This is the early 21st century, when humanity began to touch, however briefly, the objects wandering between the stars. And this is only the beginning. In the cold darkness beyond Neptune's orbit, 3 Atlas races onward. Its coma has faded, its tail dissipated. The sun is now just another star in its sky. No brighter than Venus appears to us. The comet carries no memory of its passage through our system, no awareness of the telescopes that watched, the instruments that measured, the humans who wondered. But we remember. The data are archived, the images preserved, the papers published. Future generations will study 3 Atlas as we study historical comets observed centuries ago. Distant events made present through records, knowledge passed forward through time. And perhaps, someday, a spacecraft bearing our name will intercept an interstellar traveler, will land on its surface, will analyze its ices, and send back the definitive answers that spectra alone cannot provide. When that day comes, the groundwork laid by 3 on Atlas, the techniques refined, the questions framed, the community organized, will be the foundation. Until then, we watch and wait, because the cosmos is patient and vast and full of travelers. And somewhere, in the dark between stars, another visitor is already on its way.